Does the earth breathe? It is a question that sits small and patient in the mind, like the ember of a thought waiting for air. It asks not about lungs and ribs, but about a larger movement, the slow and staggered inhalations and exhalations of an entire planet. It asks whether the rhythms of atmosphere and ocean, of ice and forest, amount to something more than chemical bookkeeping, a pulse, a respiration, a living cadence that can be felt, measured, and, perhaps most unnervingly, altered. To imagine the earth breathing is to reframe familiar phenomena. Wind is not merely air on the move, it is the outward sighing of an atmosphere adjusting to heat, to pressure, to the uneven illumination of a tilted globe. The ocean's surface is not merely waves and spray, it is the wet skin of a body that inhales carbon and exhales heat. Clouds are the exhalations condensing into visible vapor. Forests and phytoplankton become alveoli, exchanging gases with the greater body, their leaves and chlorophyll doing the microscopic work of taking in carbon and releasing oxygen. In this frame, respiration is not a private act of organisms, but the aggregate of countless exchanges across scales, from the microsecond opening of a stomatal pore to the millennium-long drift of ocean currents. There is a temptation, in saying this, to make the metaphor literal, to imagine a planet drawing breath like a sleeping mammal. That would be misleading. The earth does not inhale with a diaphragm, it breathes with processes. Yet metaphors are meant to reveal rather than deceive. If lungs are defined by exchange, by taking in one mix and letting out another, by regulating internal chemistry in response to external conditions, then atmosphere and ocean perform the same function for the planetary system. Atmosphere takes in water vapor, aerosols, gases. It distributes heat. It responds to the chemistry of life on the surface. Ocean absorbs heat and carbon, moves it across basins and depths, and stores memory in its layers. Together they regulate climate, chemical balance, and hence habitability. To feel this planetary breath is a different proposition entirely. Human experience compresses long durations into sensations. The simplest immediate ways to feel earth breathing are sensory and intimate. On a cliff edge, the wind slapping against the skin is a sudden reminder that the atmosphere is in motion. The gust has a source and a destination. It is a redistribution of energy and momentum, a small convective movement. In a forest, the air smells of resin and leaves after rain, the scent of volatilized compounds released when stomata reopen, when soil microbes react to moisture. On beaches, the rhythmic push and retreat of waves is a tidal exhale, ceaseless and patient. In winter, the creak of sea ice contracting and a thunder of calving glaciers are deep, slow inhalations and exhalations right in ice and sound. These sensory instances are immediate, but many breaths are quieter, spread across months and years. The coast experiences sea breezes daily. Land heats faster than sea, causing air to rise over land and pull a cool current in from the ocean. A diurnal breath. Forests have a day-night heartbeat. During daylight, photosynthesis sequesters carbon and releases oxygen, creating a modest daytime exhalation of oxygen and uptake of CO2. At night, respiration predominates and the balance tips. In temperate regions, the rhythm is seasonal. Deciduous trees spray leaves each spring and take them back in autumn, an annual respiration of green and decay, a cycle in which carbon is inhaled and later exhaled into the soil and atmosphere. Beyond seasons, there are breaths measured in years and decades. The El Niño southern oscillation is a planetary sigh with consequences, an episodic rearrangement of sea surface temperatures and trade winds across the Pacific that sends shockwaves across weather systems, fisheries, and human societies. Monsoon cycles are massive inhalations and exhalations of moisture, drawing clouds inland for months and releasing them as rain, feeding billions of people and 1,000 different ecologies. On longer timescales, the deep ocean circulates like a slow cardiovascular system, the thermohaline conveyor moving warmth from equatorial waters to higher latitudes and drawing down carbon into its dark depths. These are breaths that a single human lifespan can only partially observe, felt as a changed pattern of storms, a rise in sea level, a shift in the places where crops can grow. Deep time reframes the question yet again. When the narrators of geology speak, in strata, isotopes, and fossil assemblages, the Earth's breathing takes on epochs. 2.5 billion years ago, a punctuated exhalation of oxygen transformed the planet during the Great Oxygenation Event. Prior to that, the atmosphere was a stranger to free oxygen. Its composition shifted as photosynthetic microbes gradually altered the chemistry of the skies. That rising tide of oxygen did not happen overnight. It was a long, cascading series of changes in which the Earth's breath turned from a reducing, methane-rich whisper into an oxygenated chorus, enabling new metabolisms, new ecologies. In contrast, snowball Earth episodes are planetary inhalations so extreme that the surface froze over, light dimmed, and the very chemistry of the atmosphere shifted beneath a lid of ice. Volcanism, tectonics, and solar input conspired with albedo to push the climate into a near-global slumber, a breath held for millions of years. The Earth survived these breath halts and exhaled again, warming and reoxygenating as the long play of geology restored balance. These deep breaths are not merely climatic curiosities, but boundary conditions for life itself. They open and close gateways to evolutionary opportunities. And then there are the abrupt strokes, mass extinctions, asteroid impacts, flood basalts, perturbations that wrench open the planetary chest and let out a choking gasp. The end, Permian extinction, marked by massive volcanic outgassing, turned the planet's breath toxic in ways that remade ecosystems. The end, Cretaceous impact, delivered a different shock, smothering photosynthesis under lashing soot and cooling the climate, while the subsequent recovery restructured the planetary respiratory system anew. These are events where the breath does not merely adjust, but is forced into a new pattern, and the resulting scars remain visible in rocks and chemical proxies long after the air has cleared. The narration of Earth's breath becomes especially eerie when considering the possibility of technogenic influence. Human industry has altered the composition of the atmosphere within a tiny fraction of Earth's lifespan. Carbon dioxide concentrations, once stable within a narrow envelope for tens of thousands of years, have surged with the burning of fossil fuels. Methane emissions have risen with agriculture and industrial processes. Aerosols from combustion and particulate pollution change the immediate character of local air and can even modulate cloud formation. The anthropogenic imprint is a kind of forced exhalation, an injection of new compounds into old rhythms. Speculatively, if an ancient civilization existed and left signatures, would those signatures be readable now? The question is both scientific and contemplative. Atmospheric signatures can be evanescent. Gases diffuse, react, and are absorbed. Some signals linger. Particular isotopic ratios in sedimentary layers, unusual concentrations of heavy metals, or anomalous microplastics bound in strata might persist across millennia. But the atmosphere itself is a quick ledger. It turns over. The durability of a signal depends on where it ends up. Gas phase anomalies are fleeting unless they alter broader biogeochemical cycles and get locked into rocks, ice, or ocean sediments. A large technogenic perturbation might leave chemical fingerprints in polar ice, in ocean anoxia layers, or in the isotopic ratios of carbon preserved in peat and coal. Yet the longer the timescale, the more likely that geology, weathering, and biological cycling will blur and bury these marks. The planet breathes, and in doing so, it erases some of its own exhalations. That capacity for erasure is a double-edged truth. It suggests that Earth is both generous and ruthless. Generous in that it can heal, redistribute, and buffer. Ruthless in that it can bury. Entire cities of biological activity have left faint chemical whispers, chalk cliffs formed by the slow accrual of coccolithophores, carboniferous coal beds, the ossified remains of swamp forests. The imprint of life is vast and legible in rocks, but the intimacies of a short-lived industrial moment are more ephemeral unless they catalyze a process that the planet records in its long-term memory. A sustained shift in carbon cycling will be written in the carbonic chemistry of the oceans, in shifts of foraminiferous shells, in the faint isotopic nudges that paleoclimatologists read like a planet's diary. To feel the Earth's breath, then, is to move between scales of immediacy and slowness, between the tactile and the tectonic. It is to stand at the shoreline and recognize the ocean's inhalation in the fog that rolls inland, the sea's breath cooled and salted, and to read the steady increase of CO2 on a graph as a different kind of exhalation, made visible only through instruments. It is to sense the hush of a winter forest as trees lower their metabolic activity, and to compare that hush to the glacial creek. That announces a much deeper, slower inhalation. Sensation and measurement become complementary modes of perception. One belongs to the skin and ear, the other to the patient accumulation of data. There is a moral resonance here, too. Humans are creatures of an instant compared to geological rhythms, yet they possess the power to alter the breath of a world. That power can provoke awe and a certain dread. The knowledge that the atmosphere's composition can be pushed toward states not seen for millions of years reframes human action as an act upon a living system. To feel culpability or wonder at the same time is a uniquely human product, an emotional reading that the planet itself cannot register but that shapes what humans do next. It is also a source of hope. If planetary breathing is a dynamic, not a fixed doom, then interventions might be possible that steer rhythms rather than smash them irreparably. The ocean will continue to circulate and sequester, forests can regrow, soils can be managed. Yet there are thresholds, tipping points where the breath changes character. Methane releases from thawing permafrost, for instance, would be an exhalation that amplifies warming, potentially altering the planet's pattern of respiration in a self-reinforcing way. The metaphor of breath becomes urgent here. It is not merely aesthetic, but diagnostic, a way to think about thresholds and feedbacks. The poet in humanity might be tempted to attribute intent to the earth, but the more illuminating posture is humility. The planet's breathing is an emergent property arising from countless interactions among geology, chemistry, and biology. Human curiosity about whether Earth breathes is in part recognition of being a passenger on something grander. To watch the planet is to watch a system that remembers and forgets, that inhales and exhales across time horizons that dwarf human institutions. In the fossil record lies a humbling inventory, ecosystems that flourished, collapsed, and reassembled, chemical states that once prevailed and have since vanished. Yet the breath is not an impersonal abstraction. Its movements shape where humans can live comfortably, how crops fail or flourish, where storms will erode coasts, and where seas will rise. The planetary respiration supplies rhythm to the human calendar, harvests timed to rainy seasons, migrations timed to monsoons, festivals layered atop annual climate cycles. In that sense, human culture itself is synchronized to certain breaths of the earth. When those rhythms change, culture strains to adapt or is lost. The feeling that something vital is being altered is not purely environmental, but deeply cultural. A loss of predictable pattern becomes a loss of memory, of habit, of identity. Speculative thought about long-buried civilizations intertwines with this idea. If a technological society had ever arisen and then disappeared, what would their breath have left? The most enduring traces would likely not be towering monuments, but perturbations in chemistry and sediment. A sudden spike of nitrogen-based fertilizers might be discoverable in soil horizons. A pulse of synthetic compounds could be trapped in amber-like resins or in compacted sediments. But the deeper point is that the planet's breathing, its atmospheric and oceanic buffering, is also a process of concealment. Sediments bury, oceans dilute, weathering scavenges. The longer the silence, the harder it becomes to read the voice that once spoke. This ambiguity is a source of tension. Paradoxically, the very processes that sustain habitability also erase the short-term excesses that disturb it. The ocean is both a sink that absorbs carbon and a slow recorder that obscures. The atmosphere is a swift ledger that returns to balance through chemical and biological cycling, unless those cycles are pushed beyond their capacities. This duality is an ethical mirror. It suggests that restoration is possible, but that the histories of excess will not be easily undone without consequence. To end the question with an image is to fall back into the scenic temptation the guidelines forbid at the opening. Instead, the proper closing is another question, a hinge into the next act. How will the future reads of the planet's breath be written, and who will interpret them? Instruments already listen, satellites that map heat and moisture, ice cores that archive air bubbles like tiny vaults, sensors that trace the faintest isotopic nudges. The earth continues to breathe in complex ways that are both carved into rock and whispered into wind. Humanity's task is to learn the grammar of that respiration, to pay attention to both the small gusts on the skin and the thousand-year convulsions in the crust, and to decide whether to be a noisy, heedless presence or a careful steward of the planet's breath. If the earth breathes, it does so without malice or joy. Its inhalations and exhalations are the sum of processes and histories. The responsibility, emotional, ethical, practical, falls on those creatures capable of reflection. In that space between knowledge and action lies a choice, to listen and respond with humility, or to continue to force the rhythm until the system rewrites what is possible. The sound of the planet's breath is subtle, vast, and inscrutable, and the most human response may be simply to stop dividing it into metaphor and reality, and instead to learn how to hear. What did the planet's first breath sound like? It is not a question of lungs or voice, but a speculative listening post, placed at the hinge between chaos and the slow articulation of habitability. The image that follows is not a scene of trees and oceans. It is an idea that the first inhalation of Earth was the making of its air, and that this making set the terms for every future exhale. And that nascent atmosphere, the chemistry of warmth and ash, steam and sunlight, would compose the opening stanza of planetary respiration. The early Earth presented itself as a newborn body still shedding the memory of its violent birth. Accretion had fused rock and metal, impacts had pulverized surfaces, and injected energy on a cataclysmic scale. Any primordial cloak of hydrogen and helium that might have clung to the infant planet was stripped by the heat and by the young sun's energetic tantrums. What remained, what needed to be fashioned anew, was a secondary atmosphere, an atmosphere grown not from cosmic inheritance, but from inside, volcanic outgassing, the slow exhalations of a molten skin cooling into lithosphere. Volcanoes were the planet's early breathers. They did not breathe with lungs or intent. They vented, erupting gases that painted the sky with steam, carbon dioxide, sulfur compounds, and 1,000 trace molecules. In every plume there was a story of deep earth chemistry. Carbon locked inside minerals freed and sent skyward. Water vapor boiled free from hydrated rocks. Sulfides and halides lifted in fine particles. The chemistry of those plumes defined a first chemistry of habitability, an atmosphere thick with greenhouse gases that insulated the surface from the faint young sun. There is a paradox here that becomes a philosophical axle. The young sun shone with less power than it does today. Calculations suggest the early star would have been dimmer by perhaps 20–30%, an embarrassment of feebleness that, if left unaddressed, should have frozen oceans solid. Yet the geological record gives no simple picture of a planet locked in ice in its earliest eons. The solution, speculative yet grounded, is greenhouse, a suffocating warmth born of steam and carbon dioxide and methane, a chemical blanket woven by the planet's own volatile breaths. Steam, water vapor, was abundant. As the surface cooled from incandescent silica into solid crust, atmospheric temperatures remained high enough that water lingered as vapor. Rain, when it finally began, arrived as a deluge that could last for thousands of years, carving basins and filling depressions until oceans pooled and spread. Before that calm, the sky glowed with a steam-laden heat where clouds were not the cottony shapes of today, but thick veils that trapped infrared, preventing quick escape of heat and keeping the young Earth warm enough for liquid water to persist once it condensed. Carbon dioxide played its role like a slow-acting furnace. Emitted in torrents from volcanic rifts and from the degassing of newly forming rocks, CO2 built an atmosphere dense and heavy. In the absence of life to sequester it quickly, CO2 could persist, dissolving into surface waters, reacting with minerals, and precipitating as carbonates under the right conditions. Here, then, began the primal outlines of the carbon cycle, a circuit between atmosphere, ocean, rock, and the deep mantle. The carbon cycle of the Hadean and early Archean was not yet the elegant, life-mediated loop it would become. It was a raw geochemical engine. Carbon stored in the mantle returned via volcanism. Atmospheric CO2 dissolved in the newly formed oceans and, when ion concentrations allowed, precipitated as carbonate minerals, building layers that would one day lithify into the rocks that preserve a planet's biography. Weathering, the chemical wearing away of rock, began as soon as rain contacted hot basalts, drawing CO2 out of the air and creating bicarbonate that rivers ferried to sea. In this way, the planet's first respiratory cycle took a primitive form, gas to water to mineral. A loop worked in mineral time rather than organismal breath. Methane was a more dramatic, if ephemeral, actor. In a world before abundant oxygen, methane could accumulate where it was produced, whether through geologic serpentinization, reactions, volcanic chemistry, or later biological methanogenesis. Methane is a potent greenhouse gas, many times more effective per molecule than CO2. In the early atmosphere, even modest concentrations of methane could multiply the warming effect, helping to steady a climate under a less luminous sun. This chemical legerdemain, the interplay of CO2, methane, and water vapor, created a greenhouse sufficiently strong to keep the surface suitable for liquid water even while solar input lagged behind. There was violence in these processes. Impacts from leftover planetesimals and comets periodically punctured the atmosphere, evaporating oceans and injecting more steam and volatile compounds. Each collision reset local atmospheres and deposited new chemical gradients, sparking ephemeral chemistry that could be incredibly rich. Those same impacts also delivered volatiles, water, and carbonaceous material that complemented outgassing as sources of atmospheric constituents. It is a dizzying cycle. The planet's first breath was not a single inhalation, but a chorus of expulsions and infalls, of volcanic exhalation and extraterrestrial delivery. Slow, inexorable feedbacks began to assert themselves. As CO2 increased, the greenhouse warmed the planet. As temperatures rose, weathering rates accelerated because wet conditions tend to chemically erode rock faster. Accelerated weathering drew CO2 down from the atmosphere more swiftly, a negative feedback that acted like a rudimentary thermostat over geologic timescales. This silicate weathering thermostat would become a principal stabilizer of climate, i.e., one reason Earth could maintain temperate conditions over eons of solar brightening. The carbon cycle, in this light, functioned as planetary respiration with an inbuilt regulator. Exhale too much CO2 and rock will, in time, inhale it back through weathering and sedimentation. Life, when it finally appeared, would interleave itself with this geochemical scaffolding in ways both subtle and profound. But before life could impose its metabolic rhythms, the planet's chemistry had to create niches of stability, pockets in the cooling crust, shallow, warm seas rich in dissolved minerals, hydrothermal vents where chemical gradients could be exploited. The chemistry of a steam and CO2 atmosphere combined with ocean chemistry to form a set of boundary conditions within which proto-metabolic networks could tinker. The first biological breaths, were they to arise, would be whispers layered onto a far older, more massive planetary inhalation and exhalation. There is also an ecological poetry in the notion that the atmosphere is both product and parent. The early atmosphere governed where liquids could persist. In turn, the presence of liquids allowed for chemical reactions that would modulate the atmosphere. The carbon cycle was the axis of this governance. When carbon was buried, whether as carbonate minerals that precipitated out of seawater or as organic matter that accumulated in anoxic basins, it was effectively pulled out of the atmospheric ledger. Subduction would later return much of this buried carbon to the mantle, and volcanism would eventually re-release it, a multi-million-year sequestration punctuated by eventual outgassing. Thus, planetary breathing happened at many tempos, the quick hydrogen exchange of molecules in the air, the seasonal dissolving and releasing of gases in water, and the deep, patient cycling of carbon through rock and mantle. Speculative documentary thought presses at boundaries. Could the chemistry of that first breath reveal traces that survive to the present? The answer is a complex choreography. Some sediments, ancient carbonate platforms, banded iron formations, certain isotopic signatures, preserve vestiges of those early atmospheres and oceans. Isotopes of carbon, ratios of carbon to carbon-12 to carbon-13, can whisper biological processing or preferential fractionation. Sulfur isotopes can hint at anoxic atmospheres and photochemical reactions that would be impossible under a modern oxygenated sky. These chemical relics are not straightforward narratives, but palimpsests, overwritten by later processes, degraded by heat and pressure, complicated by tectonics. Yet they are legible enough that modern geochemists reconstruct a portrait of an atmosphere evolving from a heavy, reducing character toward an oxidizing one, a transition that itself rewired the planetary respiration. When the narrator speaks of fire, steam, and greenhouse gases, there is a temptation to dramatize. But the more interesting drama is slow and cumulative. Fire, in the sense of volcanic and impact heating, forged conditions, steam, the atmosphere's water vapor, modulated heat, greenhouse gases, chiefly CO2 and methane, held warmth in place. Together they composed an atmosphere that made Earth habitable at a time when it could have been simply inhospitable. The first breath was both generous and precarious. It created surface conditions where chemistry could organize into complexity, but it could also flip toward extremes. Too much greenhouse, too long, and chemical pathways toward habitability might close. Too little, and oceans would freeze and chemical richness would become locked beneath an ice sheet. To imagine this era is to be struck by a sensation of smallness and brevity. Human history sits as an almost impossible dot against these processes. The memory of the atmosphere's first breath is preserved in rocks counting time in millions and billions of years, indifferent to human narratives. Yet the emotional response to understanding such scales is not merely numerical amazement. It carries a reflective sorrow and a peculiar humility. The planet's early atmosphere was not constructed for humanity. It was a set of conditions that allowed, by accident and by geochemistry, for life to try its fortunes. That realization frames human stewardship in a different light. The early breaths that made life possible were not repeatable acts of generosity, but contingent outcomes of violent and stochastic geophysical processes. There is also, however, a note of wonder that arises from the idea that the planet could engineer such a delicate balance. The silicate weathering feedback, the dissolution of CO2 into oceans, the precipitation of carbonates, these are mechanical, physical processes. Yet they collectively formed a planetary scale control system that, over vast durations, maintained habitability. It is tempting to read intentionality into this system, to attribute homeostasis, but the more accurate stance is to recognize emergent stability, order born from the interactions of many parts without any central governor. As the narrative shifts toward the present, the carbon cycle remains central. The same circuit that began in the planet's first atmospheres continues to govern climate. Human activity, the rapid extraction and combustion of ancient carbon, pumps CO2 into an atmosphere that has been, for most of geologic memory, in a different band. The timescales differ, where volcanoes and weathering trade carbon over millions of years. Combustion and industrial emission have altered the balance over mere centuries. Here again appears the tension between the deep, slow breathing of Earth and the sudden, sharp exhalations introduced by a single species. If the first breath defined the chemistry of habitability, modern perturbations test the resilience of a system that was never meant to be forced so abruptly. The carbon cycle will respond through increased weathering, ocean uptake, and eventual sequestration in sediments, but these responses occur at the glacial pace of geology. In the meantime, atmospheric composition, ocean chemistry, and climatic patterns shift. The story of the first breath thus reads forward into a narrative about responsibility. Understanding the genesis of the atmosphere clarifies how easily its composition can be altered and how consequential such alteration is. The speculative mind lingers on the archival capacity of the planet. Some records of the first breath endure. Ancient zircons that betray liquid water existed early, isotopic anomalies that suggest atmospheric chemistry different from today. But much is lost. Impacts, subduction, metamorphism erase and obfuscate. The planet breathes and forgets. That double property, to create and to efface, is a recurring theme. The first breath is both origin and ephemeral trace. Interpreting it requires instruments and imagination, satellites that read modern compositions, mass spectrometers that parse isotopes in ancient rocks, and a narrative sensibility that can translate geochemistry into an account of planetary respiration. The closing hinge of this section is not an image, but another question, one that transitions between the primordial panorama and the ongoing story. If the first breath set the chemistry of life, what obligations does that origin impose on continued practice? The question reframes ethics in geologic terms. It asks who will read the ledger of the carbon cycle, who will learn the grammar of planetary breathing, and how those listeners will choose to act. The answer is not prescribed by rocks. It is a human answer, contingent on courage, curiosity, and a willingness to fit short human projects within the context of a slow, powerful, planetary exhalation. In that way, the early world of fire, steam, and greenhouse gases is not a remote tableau, but an ancestral chapter of a book still being written. The planet's first breath was a chemical and physical performance that made complexity possible. Reading it is both a scientific reconstruction and an act of humility, a way to remember that human time is thin against geologic atmospheres, and that the carbon cycle cycles on, vast and patient, indifferent to any single yet susceptible to collective action. The task of interpretation, of stewardship, and of reverent attention remains. The narrator leaves this idea suspended, like a held breath ready to exhale into the next act. The emergence of life and the ways living processes would fold themselves into the planet's respiration. What holds a planet together when its breath grows long and slow? It is a question that pivots attention away from atmospheres and oceans and toward the solid scaffolding beneath them, the structural geometry that gives the world a form, a tension, and a protocol for how its chest may expand and contract. If atmosphere and ocean supply the gas of breath, then geology supplies the ribs, mountain chains, continental shields, ocean basins, a planetary ribcage assembled over eons by forces that operate at a pace almost designed to outlast curiosity. The concept is simple and then vast. The outermost shell of the Earth is not a single continuous skin, but a mosaic. Rigid lithospheric plates float, creep, collide, and separate atop a softer mantle. Beneath them, the asthenosphere, warm, ductile rock behaving like a viscous fluid over geological timescales, convex. This convective motion, driven by heat stripped from the deep mantle and by differences in density within the shell itself, is the unseen heartbeat of plate tectonics. The plates move in a choreography measured in millimeters to centimeters per year, But over millions of years, these increments compose continental journeys and oceanic transformations. The ribs of mountains and ocean margins, therefore, are not static props. They are living seams sewn by the slow hand of the planet. There are three basic seams where plates interact, and each thread stitches a different aspect of the rib cage. Where plates diverge, new crust is born along mid-ocean ridges. Magma wells up, solidifies, and pushes older lithosphere aside, a slow widening of the planetary chest that opens space for oceans to deepen. Where plates converge, one plate may be thrust beneath another in subduction, or two continental masses may collide and crumple, raising mountain ranges as if the chest were compressed until ribs buckled and folded. Between them, transform faults, accommodate lateral slip, a scene that slides rather than tears, and which releases energy in abrupt bursts, earthquakes, the arthritic creak of a living frame. Mountains are the most conspicuous ribs. They arise not simply as decorative crumples of the surface, but as boundary markers of plate interaction. A convergent collision folds crustal lengths into orogenic belts. Slices of oceanic plate are thrust under continental margins, releasing volatiles that feed volcanic arcs and sculpt high relief. In places where continents collide head-on, such as when two buoyant masses meet, crust thickens and thrusts upward. This uplift is painfully slow on the human clock, typically measured in millimeters or centimeters annually, yet persistent climbing reshapes climate, river networks, and ecosystems. Over tens of millions of years, a mountain chain can rise to alpine dignity and then wear down into a chain of soft hills. The ribs are continually reshaped, their peaks smoothing under rain and storms, their flanks shedding sediment to basins below. Those basins, plains and sedimentary lowlands, are the softer connective tissue between ribs. They are the spaces where erosion deposits what uplift creates, the places where rivers splice the highlands to the sea, where deltas accumulate, and where soils develop to host ecosystems. Plains do not command the same dramatic rhetoric as mountains, yet they are vital components of the rib cage. They moderate motion, collect memory. Sedimentary basins are archived in their layers. They record floods and droughts, glacial advances and retreats, and the slow input of life. Their sediments are the planet's memory cards, compacting into strata that scientists read to reconstruct atmospheric chemistry, sea level, and even the occasional planet-scale catastrophe. Oceans are the intercostal cavities, vast and mobile spaces that breeze with the atmosphere in intricate feedback. The opening and closing of ocean basins is itself a tectonic consequence. When mid-ocean spreading widens a basin, heat and circulation patterns shift. When oceanic crust is consumed at subduction zones, basins, coasts, and continents so often unite into supercontinents. The configuration of ocean basins, their depths and widths, controls continental weathering rates, alters ocean circulation, and in doing so modulates the planet's long-term carbon balance. A chest wider open to heat exchange can, in geological terms, change how the planet holds its breath. It is in the mechanics of creation and destruction that the rib cage exerts its deepest influence on planetary breathing. New crust forms at ridges and is recycled at trenches. Continental margins grow by accretion and are reworked by subduction and collision. This continuous creation and consumption is the slow maintenance of habitability. Volcanic eruptions expel gases long sequestered within the mantle: carbon dioxide, sulfur dioxide, water vapor. Emissions that can be read as tectonic exhalations. Conversely, uplift exposes fresh rock to weathering. Chemical weathering of silicate rocks removes CO2 from the atmosphere on timescales of hundreds of thousands to millions of years, locking carbon into bicarbonate in rivers and ultimately as carbonate minerals in the sea. That weathering is a kind of rib cage mediated inhalation, drawing the breath of carbon back out of the air into mineral form. There are clear, necessary feedbacks embedded in this architecture. If the planet warms, weathering tends to accelerate, water flows more vigorously, chemical reactions proceed faster, more rock is dissolved. That enhanced weathering draws down atmospheric CO2, tending to cool the planet. If the planet cools, weathering slows, CO2 accumulates again from volcanic outgassing and the climate warms. Over hundreds of millions of years, plate tectonics sets the pace for the silicate weathering thermostat. The rib cage matters because its movements determine where fresh rock is exposed and how quickly it is transported to the ocean, thereby modulating a vital component of the carbon cycle and, with it, the global breath. Plate tectonics is also a principal agent of erasure. Oceanic crust, created at ridges, lives only tens to a few 100 million years before it is subducted and recycled. Any artifacts, chemical signals, or records on such crust are routinely swallowed and mixed into the mantle. Continental crust survives longer, especially the ancient cratons that form stable cores, but even continents are reworked. Margins are blasted by rifting, sutured in collisions, and ordered by the slow machinery of erosion. The ribcage does not merely protect, it recycles. It buries and distorts. For anyone searching for traces of a short-lived surface phenomenon, this is a sobering truth. Much that lies upon the moving plates will be drawn back into the kiln of the earth, transformed into rock, and eventually into magma. The dynamics of plates are not monolithic. Slap pull! The gravitational force exerted by a cold, dense plate sinking into the mantle is a powerful driver. Ridge push, the force exerted by the creation of new lithosphere at elevated mid-ocean ridges, contributes. The viscosity contrast between lithosphere and asthenosphere allows for decoupling and lateral motion. Where mantle plumes rise, localized upwellings create volcanic hotspots and, sometimes, flood basalts. Sudden outpourings of enormous volumes of basaltic lava that can alter atmospheric chemistry within timescales short enough to destabilize biospheres. These flood basalts have been implicated in several mass extinctions. Here the ribcage does not merely flex, it coughs, spewing material and gas in a planetary perturbation. That tension between the slow and the abrupt is central to any attempt to read the Earth's breath in geological structures. Orgentic rise is slow enough to be invisible in a human life, yet an LIP can assert its presence within tens of thousands of years. Subduction zones deliver their remembered load of crust and sediments to great depths, liberating volatiles under pressure to be recycled into magmas. In plate margins, the chemical state of the atmosphere can be altered as if by lung gasp. Large volcanic episodes inject sulfur aerosols into the stratosphere, reflecting sunlight and cooling the planet temporarily. Volcanic CO2 accumulations can, over longer terms, strengthen greenhouse warming. The ribcage is therefore both a regulator and a potential agent of climatic surprise. Mountains also sculpt weather in immediate, local ways that compound their global effects. An orogeny will reroute winds, create rain shadows, nurture monsoonal regimes, and force atmospheric circulation into new modes. The uplift of a major mountain belt can strengthen seasonal precipitation patterns on continental scales, reorganize vegetation belts, and thereby alter biological carbon storage. Rivers born in mountains become conveyors of eroded rock and organic carbon to the sea. Deltas form at their mouths, trapping carbon-rich sediments that are ultimately buried. The ribcage shapes where life will flourish, where soils will form, where people, where any complex surface occupant can find sustenance. Human narratives naturally shrink before these timescales, but they remain responsive. Human cultures have always mapped themselves onto the contours of this ribcage, valleys as corridors, highlands as refuges, coasts as portals. Yet the long memory of geology sees beyond these ephemeral patterns. Plate reconstructions reveal continents closing and opening, supercontinents assembling and fragmenting in cycles that last hundreds of millions of years. The Wilson cycle, the opening and closure of ocean basins, has been a fundamental heartbeat of continental migration. Supercontinents change the geometry of shallow seas, reorganize ocean currents, and alter the distribution of life. They change the breathing apparatus of the world. This is where the emotional quality of the landscape, the sense of weight, of endurance, of slow violence, becomes legible. The planet's ribcage is patient, indifferent, and relentless. It offers stability for long spans in the form of cratonic shields, yet it also enacts transformations that demolish and rebuild, sometimes gentle, sometimes catastrophic. The same processes that raise a mountain will later send its material to the depths, where it will be reheated and, perhaps, degassed in future volcanic episodes. Any single feature is always provisional, a temporary architecture in an ongoing remodeling plan. That provisional nature carries an ethical implication that matches the earlier reflections on atmospheric breath. If much of the planet's surface is subject to recycling, then the archaeological footprint of a brief technogenic flourish might be shallow indeed, unless it catalyzes changes that the ribcage records in deeper ways. A massive perturbation of carbon cycling, for example, can alter weathering patterns or ocean chemistry in ways that will be preserved in sediments and isotopes. The ribcage does not erase everything with equal fluency. It records global shifts in the chemical boundary conditions of surface processes. Thus tectonics both buries and archives, erases and inscribes. It is a complex librarian with a bias toward the grand and persistent. The narrator might pause to consider sound. Geological movements, for all their slowness, manifest in sharp acoustics when they suddenly release energy. Earthquakes are the cracking of ribs, the groan of a thrust fault, the snap of a transform, the low rumble under a volcanic flank. These are immediate reminders that beneath the pretense of solidity, the ribcage is not a passive frame, but a tense system waiting to rearrange. Tsunamis generated by subduction earthquakes are the most dramatic evidence that the coupling between solid plates and oceanic cavities can translate a subterranean adjustment into a planetary scale movement of mass, an ocean's inhalation and exhalation, with social consequences stamped into human time. Geological structure is also the primary mediator of the planet's capacity to conceal. Subducted materials are mixed, metamorphosed, and at great depth lose the chemical signatures of their origin. The longer a signal needs to persist through time, the more likely it is to be transformed into something less recognizable. Continental crust offers a longer gestational period for records, yet even its surface is subject to erosive scouring, sediment burial, and thermal alteration. Underneath, cratons preserve the most ancient registrations. Shield areas, with rocks hundreds of millions to billions of years old, are the resilient bones in the rib cage. They hold in their isotopic ratios and structures a faint but durable archive of early planetary breaths. In speculative terms, plate tectonics imposes a severe constraint on the detectability of transient surface phenomena. A short-lived civilization, no matter how loud in its own time, would have to produce changes that either alter global biogeochemical cycles or be preserved in sediments that avoid subduction and substantial metamorphism. In other words, the ribcage cares not for novelty unless novelty is large enough to rewire the machinery of global exchange. Otherwise, it will respire gently over it, fold it into sediment, ferry it into deeper stores, or simply grind it down. From the vantage of deep time, the human impulse to leave durable marks is both understandable and hubristic. The ribs will rearrange, and the chest will assume new geometries. Yet this fact is not an argument for futility. Rather, it reframes stewardship. Understanding the mechanics of the ribcage, where uplift will expose fresh reactive rock, where subduction will swallow oceanic plate, where erosion will concentrate nutrients and carbon, is crucial to anticipating long-term outcomes of present perturbations. Geology provides limits and possibilities. It does not dictate destiny in moral terms, but offers a map of what can be influenced and what must be respected. There is a final, uneasy beauty here. The ribcage is both instrument and archivist. It builds mountains that shape climate and life. It carves basins that preserve memory. It opens and closes oceans that change. The geography of breath. To stand within this architecture is to be made aware in bodily metaphor of fragility and continuity. The planet's long breath is the interplay of gas and stone, of fluid mantle and rigid crust, of uplift and burial. To read it requires patience, instruments, and humility. It also requires imagination, transforming measurements into narrative, into the story that links the physics of plates to the smell of rain in an uplifted valley, to the presence of coal seams formed under different skies, to the trace element anomaly in a distant sedimentary layer that might chronicle a past episode of volcanic outgassing. The question that closes this section is not new, but necessary. If the ribcage is the structure that governs the planet's capacity to breathe, then who will learn to read its seams and interpret its coughs? The answer will be found in the slow institutions of science and stewardship, and instruments that measure the subtle rise of a mountain range and the faint isotopic nudges in ancient rocks, in the sharing of narratives that translate data into collective decisions. Plate tectonics will continue indifferent to any single species, yet the wisdom of those species will determine whether their actions harmonize with the deep machinery of the world or test its thresholds in ways that provoke abrupt planetary scale responses. The planetary ribcage is not merely a poetic conceit. It is the structural logic through which mountains, plains, and oceans regulate climate and habitability, archive history, and erase the short-lived. To imagine the Earth's breath without considering the frame that shapes it would be to listen to a voice without feeling the chest. In the continuing story of a breathing planet, the geometry and movement of crustal plates are the slow metronome upon which the rhythms of atmosphere and ocean are composed. What does it mean when the Earth's breath changes color? It is not merely a shift in metaphor. It is an account of the planet's atmosphere and surface rearranging their palette from the chalk white of continental ice to the verdant, cloud-swirled green of greenhouse intervals and to the murky charcoal of anoxic oceans. Color here is shorthand for state. Albedo and ice cover, aerosol loading and cloudiness, phytoplankton blooms and dust storms. The planet's inhalations and exhalations do more than move air and heat. They repaint the world, changing what reflects light and what absorbs it, altering the very impression of the planet when viewed from near space or inferred through chemical proxies. To understand that chromatic respiration is to follow threads of cause and effect that bind orbital geometry, greenhouse chemistry, ocean circulation, and biosphere dynamics into a single composite organ. Ice ages are the long, slow inhalations. They are breaths held for tens of thousands to millions of years in which the planet pulls heat inward and locks it beneath continental shields of ice. The pale, bright signature of an ice age is a high albedo state. Vast expanses of reflective ice and snow return solar energy to space, cooling the surface and reinforcing the cold. This is the most literal way the planet changes color. A whitening of the chest that alters circulation patterns, rainfall belts, and the habitats available for life. But whiteness is also a function of subtle chemistry and physics. Atmospheric dust, volcanic aerosols, and the distribution of vegetation modulate albedo. Sea ice changes the reflectivity of oceans. Cloud, microphysics can tip a region toward brightness or darkness. An ice age is therefore not only cooler, it is visually and chemically distinct. Those prolonged inhalations are rarely gradual monotones. The planet's chest rises and falls according to a nested set of rhythms, Milankovitch cycles. The slow variations in Earth's axial tilt, eccentricity, and precession act as the metronome for glacial interglacial swings. When orbital configurations favor colder summers and high latitudes, snow persists through the warm season. Persistence becomes accumulation. Ice sheets thicken, grow outward, and increase planetary albedo. Feedbacks transform a modest orbital nudge into a self-reinforcing cold epoch. Ice begets reflection. Reflection begets cooling. Cooling allows further ice accumulation. Dust, picked up from exposed continental shelves or arid lands, settles on snow, altering albedo locally and influencing melt rates. The more dust on ice, the more it darkens, the more it absorbs heat, and the more localized melting can undermine broader glaciation, a small counterpoint in a grand inhalation. Greenhouse periods are the opposite gesture, extended exhalations that warm the planet, folding atmosphere and ocean into a wetter, denser, greener embrace. In these states, albedo dims as ice retreats, seas absorb more solar radiation, and the atmosphere fills with greenhouse gases that trap outgoing infrared. The color of a greenhouse world is not a single pigment, but an ensemble. Deeper blues where open ocean replaces ice, brighter greens where forests and phytoplankton thrive, and often a haze, the optical signature of enhanced humidity, aerosols, or volcanic emissions. The Paleocene, Eocene, thermal maximum PETM, is a striking example. A rapid spike in temperature accompanied by ocean acidification, shifts in carbonate preservation, and a global rearrangement of ecosystems. It reads as a planetary exhale so warm and humid that carbonate chemistry in the oceans altered enough to leave an unmistakable isotopic trace. The mechanisms that stain the breath come in interlocking loops. Ice albedo feedback is perhaps the most immediate. More ice equals more reflection and cooling, less ice equals more absorption and warming. But greenhouse gases, principally carbon dioxide and methane, are the agents that can push the breath from pale to green. CO2 concentrations act like a tuning knob for global temperature. Methane acts like a quick, potent flare. Methane released rapidly from destabilized permafrost or gas hydrates can amplify warming in a matter of decades, whereas CO2's influence persists for centuries to millennia, diffusing into ocean reservoirs and sedimentary sinks only slowly. Vegetation itself modulates the palette. Forests sequester carbon and darken surfaces relative to grasslands or snowfields. Phytoplankton blooms can change ocean color on scales visible to satellites, while their biology mediates carbon export to the deep sea. Ocean circulation weaves through these dynamics as well, controlling heat distribution and carbon sequestration. When thermohaline circulation is vigorous, it ventilates the deep ocean, transporting dissolved carbon to depths where it is buffered, and it moves heat poleward, helping to moderate climate extremes. If circulation slows or shoals, whether through freshening of surface waters, stratification induced by warming, or disruption of wind patterns, the deep ocean can become a reservoir of warmth and anoxia. Anoxic events manifest as dark, organic-rich sediments and chemical proxies of oxygen depletion. These ocean color changes transform the planetary breath. Oxygenated exhalations give way to suffocating methane, prone puffs that amplify greenhouse conditions. Abrupt events punctuate these longer cycles. Heinrich layers, marked by ice-rafted debris dropped into the sea during massive iceberg discharges, announce episodes when ice sheet instability reshapes ocean salinity and circulation. Dansgaard, Oshger events, rapid warming events recorded in Greenland ice cores, show how a region can warm dramatically over centuries and then readjust. The Younger Dryas is a cautionary example. A sudden glacial re-advance, possibly triggered by freshwater perturbation in the North Atlantic, a swift planetary inhalation after an interglacial exhale. Such abruptness underscores a key reality. The Earth's respiratory system contains thresholds. Cross one subtly, and the planet can jump into a different color regime. The signatures of these chromatic respirations are read through a variety of proxies, each a translator of past color into measurable data. Polar ice cores trap air bubbles, snapshots of ancient atmospheres that preserve greenhouse concentrations and aerosol loading on seasonal to glacial timescales. The isotopic composition of oxygen within ice and marine carbonates, the ratio of heavy to light. Isotopes is a thermometer and a recorder of hydrological change. Heavier ratios indicate colder conditions and more ice volume. Lighter ratios suggest warming and enhanced melting. Foraminifera shells and sediments preserve isotopic stories of seawater temperature and chemistry. Pollen archives reveal shifts in vegetation cover that alter albedo and carbon storage. Lowest strata and dust layers speak to aridity and wind intensity. Trace metals and organic biomarkers can signal episodes of anoxia, methane seepage, or massive organic burial. Taken together, these archives allow a reconstruction of how the planet's breath changed color across deep time. There is a political urgency nested inside the science. Humans, unlike orbital cycles or geologic heat, can change atmospheric chemistry on timescales comparable to a single generation. The contemporary injection of CO2 is steep by paleo standards. The resulting color transition from the Holocene's relatively stable blue-green to a brighter, more humid, and potentially cloudier greenhouse state risks outpacing the adaptive bandwidth of many ecosystems. Species adapted to Ice Age cycles did so under rhythms paced by orbital forcing and long feedback times. The suddenness of anthropogenic forcing complicates migration, adaptation, and survival. Coral reefs bleach, permafrost soils darken as vegetation invades previously frozen ground, dust storms bloom over landscapes, stripped by erosion, changing optical properties on regional scales. The color shift is not only aesthetic, it is a visible metric of shifting habitability. Feedbacks can conspire to make such shifts self-reinforcing. Warming melts ice, reducing albedo and causing further warming. Thawing permafrost releases methane and CO2, which amplify warming in a positive feedback loop. Ocean stratification limits nutrient recycling to surface waters, suppressing phytoplankton productivity and weakening the biological pump that draws carbon into the deep ocean, a reduction that can increase atmospheric CO2 and, with it, warming. In some cases, protracted warming leads to ocean deoxygenation, which in turn fosters the preservation of organic carbon in sediments. Paradoxically, the burial of organic carbon can be a slow, negative feedback on atmospheric CO2, but only after a period in which anoxia causes ecosystem collapse and mass extinction. The palette of the Earth's breath thus contains its own contradictions, pathways that both amplify and attenuate change. Sometimes on disguised timescales, one of the most unnerving implications of the breathing color metaphor is the way it obscures and reveals past activity. A greenhouse world can dilute and disperse technogenic markers more rapidly than a glacial one. Increased weathering and enhanced biological productivity may lock anthropogenic carbon into sediments differently than a cold, ice-dominated state would. Ice ages, by contrast, can entomb atmospheric signals in ice cores with exquisite fidelity, but also grind and erode surface artifacts. This duality has consequences for speculative questions about any earlier transient technological civilizations. The detectability of their industrial exhalations would depend on which color the planet was wearing afterward. A long interval of whitened respiration might preserve air phase signals in ice, yet the same glacial mechanics would crush and recycle surface remains. A greenhouse aftershock could pump chemical signatures into ocean, anoxia layers and black shales, scattering through sedimentary archives that survive geological time, but the very intensity of the biological and chemical. Alterations in such events complicates attribution. Instruments are now the ears and eyes that translate these chromatic respirations into narrative. Satellites measure albedo and ocean color, tracing phytoplankton blooms and sea ice extent. Spectrometers register atmospheric trace gases, charting the contemporary march of CO2, methane, and aerosols. Paleoclimatologists read isotopic ratios and elemental abundances in cores that are time capsules of the planet's hues. The documentary task is to synthesize these readings into a sensibility, to make the long breath audible and the color shifts legible. The story that emerges is not only a chronicle of physical processes, but an ethical mirror. The planet's color changes recast human choices in terms of paleontological consequence. There is also a moral inevitability in timings. Geological respirations operate on scales that render human lifetimes brief and fragile. Yet humans can and have altered breathing patterns. The crucial question is rate. Can the biosphere and the processes that sequester carbon respond fast enough to re-establish a comfortable palate? Geological history answers in mixed tones. The planet has shifted from greenhouse to icehouse and back, with dramatic consequences for life. It has survived PETMs and mass extinctions, and yet bears the scars as red beds and black shales. That survival is not a guarantee of continuity for specific ecosystems or cultures. Color changes in the Earth's breath are, in effect, changes to the stage on which life performs. Species will reap the consequences of those shifts differently. To bring this to a human point of perspective is not to anthropomorphize the planet, but to acknowledge how intimately culture has been keyed to a particular set of climatic colors. Agriculture, settlement patterns, migration routes, and civilizational rhythms are tied to relatively stable seasons, predictable monsoons, and the memory of rainfall. When those rhythms alter, the cultural fabric strains, harvests fail, food webs unravel, coastlines retreat beneath rising seas that have, in color, become deeper blues. The emotional register this elicits is complex. It blends awe at a living planet's dynamism with dread at the fragility of human scaffolding in the face of such dynamism. The narration calls for humility, a recognition that the chest upon which humanity depends has been breathing long before and will continue breathing long after, and for something more active, stewardship that respects the tempo and thresholds of planetary change. There is a final, sobering note. Because the planet's breath can shift color dramatically, and because its processes both conceal and preserve, the legibility of human action in the geologic record is ambiguous. Carbon isotopes, trace metal anomalies, and novel organic compounds might persist in sediments and ice. Yet many markers of industrial activity, buildings, roads, ephemeral plastics, are much more vulnerable to the grinding gears of glaciers and the burying, diluting vastness of ocean basins. In other words, the planet's capacity to change color and atmosphere is both a recorder and an eraser. The whitened inhalation of an ice age can entomb air bubbles like time capsules while simultaneously obliterating surface architecture. A greenhouse exhalation can deposit chemically unusual layers, but can also overrun signals with biologically mediated noise. This ambivalence should temper hubris. The desire to leave a permanent mark collides with a planetary habit of repainting itself. The question that ends this section is not technical but ethical and interpretive. If the Earth's breath will continue to change color, who will be the readers of its hues, and how will they act upon what they see? The instruments exist, and the proxies are legible. The challenge is to translate knowledge into choices that respect the slow machinery of planetary respiration. The narrative posture required is not despair, but attentive humility, a willingness to align human projects with planetary rhythms rather than to force the chest into a different cadence. To listen to the changing color of the breath is to recognize both the fragility of the present and the profundity of deep time. The planet will continue to inhale and exhale, to whiten and to green and to darken. What is asked of humanity is to learn the grammar of those changes and, with care, to avoid pushing the breath past thresholds from which the next color change may be catastrophic and irreversible. What constitutes the first lung of a planet? It is not a single organ nor a single event, but an emergent function borne by countless tiny organisms that change the chemistry of surface environments. In that sense, the planet's earliest breaths were taken not by grand organs but by biofilms, thin, green carpets of life that lay across tidal flats, shallow shells, and the margins of primordial seas. These were the cells that learned to harvest light and, in the process, rewired the chemistry of the world. The story begins with a quiet, astonishing innovation, the harnessing of photons to do chemistry. Among the earliest practitioners were microbes that, in their metabolic experiments, discovered how to use sunlight as a source of energy. At first, many of these chemistries produced byproducts suited to a reducing world. Hydrogen sulfide was breathed out by organisms that thrive where iron and sulfur dominated the chemistry. But then, at some point, a lineage developed a different trick. It split water. This biochemical leap was modest in scale and monumental in consequence. The splitting of H2O released a tiny, invisible molecule that would, given time and cumulative production, transform skies and seas. Molecular oxygen. Cyanobacteria, the familiar archetype of those early oxygen producers, did not appear as singular, triumphant actors. They were filamentous mats and mucilaginous films, communities that held sediment, trapped light, and created steep chemical gradients at their surfaces. The immediate environment around a mat could be a study in contrasts. In daylight, the mat exhaled oxygen into the water, creating an oxygen-rich veneer centimeters thick. In darkness, the same mat reverted to respiration, consuming oxygen and releasing carbon dioxide. Within the tidal ebb and flow, these mats were local lungs, pockets of gas exchange, microscopic alveoli operating in shallow pools. To imagine them as lung cells is not mere metaphor. The colonies formed layers and structures that maximized exposure to light and to the interface between water and atmosphere. Many mats built stromatolites, laminated. Columnar accretions formed as layers of microorganisms trapped mineral sediments and precipitated carbonates. These stromatolites stand in the rock record as fossilized witnesses, internal laminations that are architectural footprints of living communities managing space and chemistry. The mat's structure increased surface area, enabling more photons to be intercepted and more gases to be exchanged. In aggregate, these microscopic strategies amounted to a planetary-scale physiology, an enormous surface area amplifier for gas transformation. But the oxygen those mats produced did not simply accumulate into a breathable sky overnight. The early Earth was a chemically hungry place. Oceans teemed with reduced iron and sulfide. Wherever free oxygen appeared, it reacted almost immediately. Iron oxidized, precipitating as rust that sank to the seafloor in the form of layered, banded iron formations. These banded iron formations, alternating bands of iron oxide and silica, are the geological signatures of oxygen's infancy, a record of oxygen being consumed as fast as it was made. For hundreds of millions of years, oxygen was not a global gas. It was a local negotiator, created in sunlit pockets and extinguished wherever sinks were available. This tug-of-war imbues the microbial story with drama. On one side were the innovators, incrementally exhaling oxygen. On the other were chemical reservoirs ready to neutralize that oxygen's reach. Methane, too, played a decisive role. In a world dominated by reduced gases, methane acted as an efficient greenhouse agent. Oxygen, once it reached sufficient abundance, would oxidize methane and thereby dim a potent warming source. The consequence is startling in thought. Microscopic photosynthesizers may have set in motion pathways that cooled parts of the planet by removing methane from the atmosphere. A biological act at the scale of a sheet of microbial mat could, in aggregate over geological time, alter the planet's thermal balance. The narrative is one of expansion and cumulative impact. Early photosynthetic life colonized new niches. It moved from submerged surfaces into shallower pools and tidal flats where light was abundant. It formed microbial carpets upon basalt flows and clung within the white heat of trailing hot springs. Each successful colonization expanded the lung of the Earth, more surface area participating in the exchange of gases. As population density increased, so did the scale of influence. That incremental growth was not linear. It arrived in pulses. Episodes of nutrient availability, changes in ocean circulation, or tectonic uplift exposing fresh rock could provide a bounty that allowed mats to proliferate. Where microbial carpets bloomed, oxygen oases formed, and in those oases new ecological opportunities emerged. Those opportunities invited complexity. Oxygen, even when only local, altered redox chemistry in shallow environments, enabling novel metabolisms to appear. Metabolic pathways that could exploit oxygen's energetic bounty were favored in the microenvironments where oxygen existed long enough to persist through dusk and tide. The presence of oxygen also drove selective pressures on those organisms that had evolved in its absence. For many anaerobic microbes, oxygen was toxic. As oxygenated niches expanded, entire metabolic guilds were displaced or forced into refugia. In macro terms, these were the first biological disruptions wrought by changing planetary breath. an ecological turnover produced by the cumulative exhalations of tiny organisms. The geological record preserves the imprint of this slow revolution. Banded iron formations, as already noted, are an archive of oxygen's early sequestration into minerals. But there are other signatures, sulfur isotope fractionations that betray the presence or absence of oxygen in the photic zone, red beds, terrestrial oxidation of iron-rich sediments, that mark the first appearance of persistent oxygen in the atmospheric column, and shifts in carbon isotope ratios that testify to burgeoning organic productivity. These are the data points by which the narrative of biospheric expansion is reconstructed, scattered, indirect, but legible to a careful reader who reads chemistry as biography. One of the most consequential consequences of the expanding oxygen supply was the formation of an ultraviolet shield. Before oxygen accumulated significantly, ultraviolet light from the sun reached the surface with greater intensity, sterilizing shallow waters and creating a harsh environment for complexity. When oxygen rose, an attendant chemical process, the formation of ozone in the upper atmosphere, began to filter the most harmful ultraviolet wavelengths. This newly formed protective veil did more than comfort life. It opened ecological space. Land, which had long been an ultraviolet exposed and dangerous prospect, became incrementally more approachable. The stage was being set, in very broad strokes, for life to contemplate conquest beyond the margins of the sea. Yet, for all of this, the oxygen story is not one of smooth progress. The accumulation of oxygen into the atmosphere unfolded episodically, punctuated by feedbacks and thresholds. Surges of oxygen production could be countered by volcanic outgassing, by widespread burial of organic carbon, or by the availability of reductants in the oceans. At times, massive burial of organic matter in anoxic seafloors resulted in net oxygenation of the atmosphere. When carbon is sequestered and not respired back to CO2, free oxygen accumulates. Thus, the biosphere's activity in producing organic matter could paradoxically drive the atmosphere toward an oxygenated state. These linkages between biological production and geological burial underscore the intimacy of biology with long-term planetary chemistry. The Great Oxygenation Event marks a dramatic hinge in this chapter. When oxygen finally rose beyond the capacity of geochemical sinks, it not only changed redox states but reorganized ecosystems and climates. The event was both creative and destructive. Aerobic metabolisms found an energetic playground. Aerobic respiration allowed for greater metabolic efficiency, a prerequisite for increased complexity. Eukaryotes, the cells with internal compartments and, later, mitochondria, found conditions that would permit their expansion. At the same time, many anaerobic lineages suffered decline or were pushed to specialized niches. The planet's respiratory character had been altered in ways that favored new evolutionary trajectories while extinguishing others. The microbial lungs had, through persistence and proliferation, rewritten the rules of habitability. There were climatic consequences as well. The reduction of atmospheric methane during oxygenation likely cooled the planet, and some researchers argue that these changes contributed to glaciations. That a microscopic community could contribute over millions of years to planetary cooling is a humbling theme. Tiny chemistries aggregated into a mechanism capable of shifting global energy balance. The atmosphere and biosphere were locked in a feedback loop. Life altered atmospheric composition. Atmospheric composition altered climate. Climate altered habitability, and habitability fed back into evolutionary possibilities. It was an emergent physiology without a central brain. From the vantage of deep time, the rise of oxygen reads as a narrative of expansion and enclosure. Expansion because life expanded its metabolic reach, occupying surfaces in greater abundance and complexity. Enclosure because oxygen's presence closed some ecological doors even as it opened others. In the rock record, this duality is visible. Oxygen-mediated mineralization preserves some compounds but erases others. Iron oxides lock chemical history into stone, while the disappearance of certain reduced minerals removes older chemical states from easy view. The biosphere performed the delicate work of creating a modern atmosphere while simultaneously erasing some of the chemical signatures of an older Earth. The metaphor of lungs is instructive because lungs do two things. They facilitate exchange, and they support a larger organism by providing a usable gas mix for metabolism. Microbial mats functioned similarly. They were exchange surfaces that transformed sunlight, water, and dissolved nutrients into organic matter and, in doing so, reshaped the composition of gases available for other metabolisms. Their work supported the expansion of ecological complexity. The raising of atmospheric oxygen enabled aerobic energy pathways to proliferate, a precondition for the later emergence of multicellular life. Yet the mat's labor was not solitary. It depended on the availability of nutrients delivered by geology, the circulation of oceans, and the physics of light penetration. In that sense, the lungs of the planet depended upon the ribs and the mantle, the broader architecture described in earlier sections. There is also a narrative of concealment. Microbial processes often leave subtle signatures. The very things that made oxygenation possible, massive organic burial, subtle shifts in isotope ratios, are the sorts of signals that could be hard to attribute definitively in isolation. The planet's breathing both records and obscures its own history. Organic carbon burial sequesters chemical evidence. Sedimentation can bury microbial fabrics beneath later deposits. Tectonics can recycle crust and metamorphose the very strata that preserved early habitational signatures. Thus, the early biosphere's work is both legible and elusive. It is inscribed in stone, yet easy to misread without the patient. Tools of geochemistry. The emotional register of this history is complicated. There is wonder at the ingenuity of life, the ability of tiny, undirected chemistries to invent a process that would alter a planet's atmosphere. There is humility in recognizing how contingent these developments were, how small changes in metabolism, chance genetic innovations, and local environmental context aggregated over eons into planetary-scale consequences. And there is a quiet unease in realizing that such a vital transformation could also be disruptive, extinguishing forms of life that had previously held ecological dominion. Finally, this chapter asks a forward-looking question. If microscopic blades of life acted as the first alveoli, expanding a biosphere that now literally breathes through the combined efforts of forests, phytoplankton, and soils, then what responsibilities follow from that knowledge? The expansion of the biosphere was not directed by foresight, but by iterative processes. Yet the present moment, where human activity can alter global gas inventories on century scales, requires a different kind of reflection. The microbial lungs took millions of years to change the atmosphere in ways that reshaped life. Humanity's capacity to alter atmospheric composition, by contrast, operates at a speed that challenges ecological buffering. Understanding the ancient choreography of photosynthesis and geochemistry becomes, therefore, not merely an account of origins, but a lesson in timescales and sensitivity. The narrator leaves this act with a sense of scale and continuation. The early biosphere had performed a quiet miracle. It converted light into chemistry and thereby converted surface habitability into a different mode altogether. The mats and their stromatolites were modest technicians in a grand planetary surgery, increasing surface area exchange and laying down the chemical scaffolding for later complexity. The breath of the living world had begun to change the composition of the lungs that would sustain future life. The question now lingers and leans into the next act. How did that altered breath cascade into ever greater complexity, into eukaryotic innovations, multicellularity, and the establishment of ecological feedbacks that would remake climate and landscapes? What if the planet's smallest, most intimate rhythm was the one that rose and fell every 24 hours, not a geological heartbeat that counts in millions of years, but a daily inhalation and exhalation that paints dawn and dusk with scent and silence? This is a different kind of breath, close, tactile, easily overlooked if one listens only for storms and tectonic groans. It is the quiet exchange between leaf and air, ocean, skin, and sky, a repeated performance in which the world reorders its chemistry with the punctuality of sunrise and the inevitability of nightfall. At morning, the earth inhales. The image is precise and deceptively ordinary. A film of dew quickens on grass. Leaves that have been stoic and shut in the dark unfurl like small sails, and the atmosphere itself seems to thin as sunlight teases open the minute gates on the undersides of leaves. Those gates, the stomata, are the planet's microalveoli. God cells change shape with subtle shifts in turgor pressure. Pores that were closed to conserve water at night open in response to light and the internal chemistry of the leaf. With that opening comes a rush, not of oxygen, but of exchange. Carbon dioxide flows inward on a gradient that plants will use to fix carbon. Water vapor diffuses outward in transpiration. In aggregate, the light-driven choreography of billions of stomata across a forest canopy or a prairie is the audible stillness of an inhalation, felt more as a change in humidity and scent than as a gust of wind. Yet the physics behind this sensation is both elegant and exacting. Sunlight excites the photosystems. Stomatal guard cells pump ions. Water evaporates into air spaces inside the leaf. and vapor seeks the lower humidity of the morning atmosphere. Evapotranspiration, the combined evaporation from soils and the transpiration from vegetation, becomes a primary mover in local microclimates. It cools leaves and soils, raises near-surface humidity, and builds the low cloud decks that will later scatter light across the day. In large forests, the collective exhalations of moisture form aerial rivers, atmospheric conveyances of vapor that can travel hundreds of miles and precipitate as rain far from their source. The Amazon basin is often described in these terms, a colossal lung whose mornings are a vast, wet inhalation that feeds storms and keeps distant regions moist. The sensory details of that inhalation are curated out of countless microscopic events. Two beads form where radiative cooling overnight drops surface temperatures below the dew point. In the first light, droplets tremble on filamentous hairs of grasses and on the glossy faces of broad leaves, catching a slow, brilliant luminescence before the sun fully warms the scene. Air that had been thin and chilled near the ground rises as the ground warms. A thin mist lifts from rivers and rice paddies, dissolving into the day's first convective currents. The smell is immediate, petrichor and the volatile organic compounds plants release as they wake. That smell is not merely aesthetic, it is a chemical broadcast, an exhalation of biogenic vapors that signal to insects, communicate with neighboring plants, and even seed cloud formation through their ability to nucleate water droplets. For all the romance, the morning inhalation is measurable. Flux towers, little instruments planted into ecosystems, act as stethoscopes. They record the downward pull of carbon dioxide into vegetation during morning photosynthetic uptake. Satellites register the greenness of canopies and the shifting patterns of moisture. Instruments like OCO, Orbiting Carbon Observatory, and ground-based spectrometers see the large-scale imprint of daytime drawdown, a diurnal signature in atmospheric CO2 that is the planet's breath translated into data. In midsummer, when the northern hemisphere's vast expanses of leafy green are fully active, that diurnal amplitude is strongest. A pronounced dip in atmospheric CO2 during afternoons, followed by a nocturnal rebound. Night, by contrast, is when the planet exhales. When light retreats, stomata close, or reduced conductance, photosynthesis ceases and the balance tips. Plants switch from net autotrophy to net respiration. Metabolism continues, and oxygen consumed in maintenance respiration yields carbon dioxide back to the air. Soil microbes, which had been suppressed by cooler, drier nights, continue their work of decomposing leaf litter and root exudates, releasing CO2 as a byproduct. The aggregate of root respiration, microbial decay, and plant maintenance breeding creates a nocturnal pulse of carbon that rises from soils and vegetation into a nocturnal boundary layer that can be physically shallow, trapping gases near the surface. This exhalation is not merely chemical, it is atmospheric theater. In valleys and basins, the night's cooling creates inversions where heavy, CO2-rich air pools. Fog can condense on these trapped layers, carrying with it the faint, sweet odor of fermenting organic matter. The nocturnal sky, once dark enough, becomes an archive of the day. It holds scent profiles, moisture, and particulates that speak of the day's metabolism. If the day felt like a collective inhalation of possibility, leaves opening and clouds forming, the night feels like a gentle, inevitable letting go, a mood of repose that carries within it the residue of a day's chemistry. There is tenderness in this rhythm and something mournful. Dawn's exhalations carry hope. Oxygen is provided, sugars are synthesized, and life's momentum gains a new stroke. Night's exhalations return what was invested. The same processes that enabled daytime abundance reconcile it into the substrate of future growth. To observe the pattern is to be made aware of cycles of giving and taking, a planet that is simultaneously generous and conservatively frugal. That emotional register, the calm of morning, the melancholic release of night, is not anthropomorphic imposition so much as a human-scale interpretation of a planetary process that every culture in some form has found ways to attune to. Dawn rituals, market hours, agricultural calendars, all are small human adaptations keyed to this pulse. But the rhythm is not uniform across the globe. Some organisms have inverted the expected cycle. Cam plants, prevalent in arid regions, open stomata at night to minimize water loss and fix CO2 into organic acids that are then used for photosynthesis by day. In desert ecosystems, the planet's breath is staggered. Day and night exchange roles depending on water scarcity. Wetlands and mangroves exhibit complex dial chemistry in which tides and salinity ionize exchanges. In urban landscapes, the rhythm is modified by surfaces that store heat and by anthropogenic emissions that inject CO2 continuously. Cities tend to exhibit a dampened biological diurnal amplitude and a persistent anthropogenic exhalation, impervious surfaces, and reduced vegetation limit the morning inhalation that would otherwise cool and freshen the air. The result is a changed cadence, a breath that is less in tune with natural cycles and more in conflict with them. Oceans, too, participate in this daily drama with their own set of gestures. Phytoplankton at the ocean's skin execute dial cycles of photosynthesis and respiration, sometimes producing oxygen in overnight oxygen minima that can be surprisingly pronounced below the surface. Surface mixed layers warm in the day, increasing stratification and reducing nutrient upwelling in some regions, which paradoxically can suppress daytime productivity and alter the diurnal oxygen cycle. At night, breathing is augmented by the respiration of heterotrophic plankton and by bacterial degradation of organic particles that sink or remain suspended. In coastal zones, the tidal rhythm overlays a diurnal one, creating patterns where the breath of a shore is a composite of sun, tide, and the metabolic idiosyncrasies of organisms dwelling in mudflats and seagrass meadows. The emotional cadence of these daily processes is amplified by seasonality. Spring's leaf out is a planetary inhalation writ large, fields and forests green in synchronized rushes, and the biosphere's capacity to pull down CO2 grows in amplitude. Autumn, when deciduous leaves fall and decomposition begins, is a long, slow exhale, a release that feeds microbes and replenishes soils but also returns carbon to the atmosphere. In boreal forests, a summer bloom of breathing is intense yet brief, an exuberant inhalation followed by a long, patient pulmonary pause during the frozen season. For humans who have lived by these rhythms for millennia, the changing tempo of breathing is woven into myth, labor, and memory. The cyclical trust that the world will inhale in spring and exhale in autumn becomes the scaffolding of calendars and economies. Technology has made these subtle breaths legible at unprecedented scales. Eddy covariance systems measure fluxes of CO2, water vapor, and heat at ecosystem scales. Networks of such towers provide a mosaic of fluxes that, when combined with satellites, reveal the planet's broad patterns of diurnal and seasonal breathing. The data can be both consoling and alarming. They show how intact forests and thriving phytoplankton can strongly regulate atmospheric composition on a daily basis. They also show how deforestation, irrigation, and urbanization can blunt or misalign those rhythms. The Amazon's daytime water vapor towers, for instance, become attenuated when forest loss reduces transpiration. Irrigated croplands in formerly arid zones can create morning fog where none existed, introducing a new human-mediated inhalation. There is a melancholic paradox in that observation. The very processes that provide sensory comfort, the smell of rain, the hush of a mist-filled morning, the cool of shade, can be diminished by actions that in other ways increase human comfort in the short term. Roads, fields, factories, and dams rearrange local and regional cycles, trading old breaths for new ones that are often less benign. In aggregate, the planet's small daily breath is thus a barometer of stewardship. When breathing is robust and patterned, ecosystems function. When it is distorted, emergent pathologies follow, microclimates shift. Species ranges move, heat waves are magnified, and hydrology is altered. The aesthetic of planetary breathing also has an archive. Many of the short-term cycles vanish without leaving a geological trace. A single day's inhalation will not be found in a rock stratum. But when a daily rhythm is altered persistently over decades and centuries, its imprint deepens. Altered vegetation patterns change albedo and can force regional climatic shifts. Persistent deforestation increases soil erosion and sedimentation rates. Changing river loads and delta formation, prolonged urban emissions alter the chemical burden of the atmosphere and can leave distinctive signatures in ice cores or lake sediments. In other words, the daily breath is ephemeral, but its chronic phases can be extended into geologic measures if human or natural forcings persist long enough. The emotional relationship humans have with this diurnal breathing is complicated by awareness. Knowledge of how the planet inhales at dawn and exhales at night can inspire a gentle humility, a desire to align human routines with natural ones. It can also produce anxiety, the recognition that altering the rhythm may have cascading consequences beyond immediate convenience. This is where the aesthetic and the ethical meet. To walk through a dew-slick forest at sunrise and feel that collective inhalation is to sense one facet of planetary health. To live in a place where the night's exhalation is replaced by continuous anthropogenic emissions is to be in proximity to a disrupted rhythm. Both experiences produce emotional responses that are culturally mediated but biologically grounded: comfort, calm, unease, mourning for lost cycles. There is also a speculative edge to consider. If long extinct civilizations ever modulated their environment, irrigating deserts, engineering forests, releasing industrial gases, they would have altered the planet's diurnal breathing in ways detectable only if those alterations were sustained. Short-lived perturbations blur into natural variability. Sustained changes imprint into isotopic compositions, sedimentation patterns, and long-term alterations of vegetation cover. The daily rhythm can therefore be both ephemeral and a sentinel. Sustained disruption of the morning inhalation and nocturnal exhalation patterns in significant regions would eventually be written into the planet's deeper archive. Listening to the planet's daily breath requires patience and tools that translate tiny chemical exchanges into a readable narrative. It requires an ear attuned to the sound of leaves, to the hiss of transpiration, to the faint electronic chirps of sensors recording nocturnal frames of rising carbon. Above all, it demands an ethical stance, a readiness to respect the tempo of a system shaped by billions of individual organisms. And by geologic scaffolding, the aesthetic pleasure of a misted morning and the melancholy of a smoky, heavy night are not mere background feelings, they are clues. They reveal the health of ecosystems and the alignment, or misalignment, of human activity with a planetary rhythm that has kept habitability within a narrow band for millennia. The narrator does not end on an instruction but on an invitation to learn to notice, to watch the way leaves react to first light, to be aware of fogs that form when the land exhales, to listen for the nocturnal hush that signals respiration and soil work. These small attentions are the beginning of stewardship. They are the human analogue of a clinician learning the subtleties of lung sounds. The planet's breath is vast and layered. It is, in one register, the sunrise opening of stomata and the evening release of soil microbes, and in another, the seasonal and climatic oscillations that accumulate into the fossil record. The aesthetic rhythm of inhalation and exhalation each day is both a poem and a measurement, a source of calm and a call to responsibility. To attend to it is not mere sentimentality, it is an act of listening that can guide choices about what to protect and how to. Temper the human imprint on a world whose breath has always been both gentle and inexorably honest. What does it mean when the planet's breathing suddenly becomes a pant, a fierce, concentrated inhalation and exhalation that reorders air, sea, and soil in a single convulsive act? It is an image and a question both. In the theater of tectonics, volcanoes are the world's heaving diaphragm, and earthquakes are the sharp intakes and convulsive exhalations that follow. Together they are a suite of strong breaths, quick, loud, sometimes short-lived, sometimes drawn out over millennia. When those breaths arrive, the small rhythms of everyday life, the day-night opening of stomata, the migration of birds, the timing of crops, find themselves momentarily tethered to something far larger and more impatient. Volcanic exhalations are emphatic. The physics are straightforward and then terrible in their consequence. Magma carrying dissolved volatiles, water, carbon dioxide, sulfur compounds, chlorine. Fluorine rises because it is hotter and less dense than surrounding rocks. As pressure falls on ascent, volatiles come out of solution, bubbles nucleate and grow, turning viscous magma into an overpressurized slurry. The release is a breath in the literal sense. Gas expands, ruptures the crust, and shoots upward as a plume. The composition of that plume determines its character. Water vapor is often dominant by mass, lending a steaming quality. Sulfur dioxide produces acrid tangs and, in the stratosphere, creates sulfate aerosols that can shade the planet for years. Carbon dioxide pools unseen, heavier than air in depressions and lethal to breathers. Halogens and acid-bearing gases seed acid rain. Ash, fragmented glass and rock, becomes the particulate punctuation of the exhalation, a grit that coats lungs, soils, and solar panels alike. To be near such an exhalation is to be reduced to elemental impressions. The first sensation is the change in the atmosphere, a pressure pulse that is both audible and tactile, a low-frequency growl that moves through the ground and through the body, felt in teeth and chest. Sound registers not just as noise but as a physical shove, the long, infrasonic rumble of a plume rising, the high-pitched tearing of an explosive column. The sky changes too, not just through dramatic ash cloud silhouettes, but through subtle optical edits. Sunlight filters through fine ash and aerosols, rendering daylight russet, elongating shadows, making distant mountains disappear behind a sepia veil. The smell is immediate and precise, sulphurous and metallic, like struck matches and briny sea air combined. Ash settles as a colorless rain, a thin concrete of dust that is both abrasive and suffocating. It abrades crops and clogging waterways, unmasks roofs and heavy-laden branches that collapse beneath its weight. Those local sensory scenes have planetary consequences. An explosive eruption injects sulfur gases into the stratosphere, where they oxidize into sulfate aerosols. These particles scatter sunlight, cooling the surface by reducing the amount of solar radiation that reaches the ground. The climatic result can be startlingly fast. A single large eruption can lower global average temperatures for a year or more, with regional anomalies that wreak havoc on agriculture. Historically recorded eruptions show how a single breath can tug at the calendar of harvests and human societies. Conversely, large-scale, prolonged volcanic activity, flood basalts that spill from fissures for tens or hundreds of thousands of years, pumps huge quantities of greenhouse gases into the atmosphere, altering the climate on timescales that intersect with evolutionary and extinction dynamics. In other words, volcanic breaths come in flavors: the cold, bright, sulfate-tinged exhalation, and the slow, heavy, CO2-rich exhalation that turns the chest warm and damp. The tectonic theater that orchestrates these breaths is the stage upon which plates diverge, collide, and slide. Subduction zones, where oceanic lithospheres dragged beneath a continental plate, are particularly fecund. As plates descend, hydrated minerals and sediments dehydrate, releasing volatiles that lower the melting temperature of the overlying mantle. Magma forms, ascends, and outgasses, creating volcanic arcs that are both conveyors of crustal recycling and pipelines for gases, stored over millions of years. Mantle plumes are another pathway. Upwellings from deep in the mantle melt the base of the lithosphere, producing massive outpourings of lava in flood basalt events. Mid-ocean ridges steadily widen basins and emit basalts and volatiles at a more subdued pace, a global background of magmatic respiration. Earthquakes are the sharp punctuation marks in this drama. They are the cracking of the ribs, accumulated strain released along faults and sudden slips. The first-order experience is startling. A deep, rolling swell can build over seconds, morph into a violent shear, and then collapse, leaving silence like a dropped curtain. The mechanical effects are immediate. Buildings sway, river channels change course, slopes fail, and liquefaction turns firm ground into quicksand. Seismically, the planet announces its convulsions in waves that circle the globe. Those waves are auditable. Seismometers read the planet's chest like instruments reading heartbeats. Very large ruptures can alter the gravitational field locally, shift coastlines by meters, and trigger tsunamis that translate a subterranean motion into a surface mass movement with social consequences in hours rather than geologic epochs. There is a peculiar coupling between earthquakes and volcanic breathing. Sometimes earthquakes precede eruptions as magma forces its path upwards. Sometimes eruptions cause seismic swarms as chambers drain and the roof collapses. In the great theater of plate interactions, a series of collapses and intrusions can produce a complex choreography, an earthquake that opens a pathway, a pulse of gas released in a tremor, the sudden clearing of a conduit that allows a breath to expand into an explosive exhalation. The scale matters. A small eruption can be a local tragedy, an ecological reset. A super eruption alters planetary climate and chemistry for decades to centuries and writes its signature into the stratigraphic ledger. That ledger is both generous and selective. Volcanic ash layers, tephra, are some of the most immediately useful time markers in sedimentary archives. A distinct ash horizon can be traced across continents, allowing precise temporal correlation of disparate records. Chemical analyses of trapped gases in glass shards tell of magma source, temperature, and volatile content. Sulfur isotopes preserved in ice cores narrate stratospheric injections long after the ash has dispersed. Yet the planet's breathing also erases. Landscapes are buried and remade, forests replaced by new soils rich in mineral nutrients, and volcanic gases alter chemical cycles, sometimes driving oxygen levels and carbon reservoirs into new configurations. The biological consequences of such breaths are complex and often paradoxical. Volcanic ash can be both a suppressant and a fertilizer. Initially, heavy ashfall smothers plants, abrades foliage, and blocks sunlight. Crops fail and water supplies are contaminated. Yet, in the medium term, ash weathering releases phosphorus and other minerals to soils and oceans. Iron-bearing ash delivered to iron-limited regions of the ocean can stimulate phytoplankton blooms, increasing biological carbon uptake and drawing down CO2, a biological reprieve after a chemical perturbation. In other contexts, acid rain resulting from volcanic halogens and sulfur accelerates the leaching of soils, mobilizing metals into rivers and disrupting aquatic ecosystems. Long-lasting flood basalt events can produce sustained greenhouse warming, ocean anoxia, and mass extinction. As seen in deep-time correlations between LIPs and biological crises, human responses to these powerful breaths have been as varied as the smells of the gases themselves. Across cultures and epochs, eruptions and earthquakes have been woven into myth and ritual. Where volcanic soils are fertile, agriculture and settlement persist despite the risk. Human communities have long chosen to live within the reach of a volcano's long-term gift of rich soils and new mineral resources, trading short-term danger for multi-generational advantage. More recently, scientific monitoring has furnished societies with predictive capability, seismographs, GPS networks, gas emission measurements, satellite thermal imaging, and infrasound arrays now act as a planetary stethoscope. These tools translate the planet's deep mechanics into warnings, tremor patterns that indicate magma movement, changes in sulfur dioxide flux that presage eruptive onset, ground deformation that signals pressurization. Yet instrumented warning is not an absolute solution. It is an attenuation, a means to buy time, to lower exposure, but never a guarantee against the planet's profound unpredictability. The effective register of living with such strong breaths is both humility and vertigo. There is awe in watching incandescent fountains of lava in the slow, inexorable flow that scours and builds. There is dread in the knowledge that the ground beneath one's feet can unmake an entire season of labor in a handful of hours. The small, daily rhythms described earlier, the opening of stomata in a canopy at sunrise, the nocturnal exhalations of soils are fragile against such powerful outbursts. A roof thick with ash can suffocate the microbes that mediate soil fertility. A sudden drop in sunlight during volcanic dimming can stress crops and ecosystems synchronized to light. The planet's strong breaths therefore have the capacity to snap open and briefly dominate the more intimate cycles that sustain local life. There is also a paradox of renewal. Volcanism creates niches as much as it destroys them. New islands arise from submarine eruptions and become laboratories for colonization. Hydrothermal systems associated with magmatic activity concentrate metals and create energy gradients exploited by specialized communities, both ancient and modern. Geothermal heat fosters fumarolic ecosystems and provides human societies with renewable energy. Volcanic landscapes are often biodiversity hotspots precisely because they are mosaics of successional stages and mineral diversity. In deep time, pulses of magmatism may serve as both drivers of extinction and as catalysts for evolutionary novelty, wiping away old assemblages and clearing ecological space for new adaptive radiations. From the standpoint of detection and archive, volcanic episodes are both revealing and obfuscating. Massive eruptions tend to leave conspicuous tephra and chemical signatures. They are stamped into ice cores, marine sediments, and terrestrial stratigraphy. Prolonged flood basalts are geologically unavoidable, their lava flows and associated gas emissions recorded across basins. But the planet's habit of recycling crust through subduction and metamorphism means that many episodes of volcanic breathing are ultimately returned to the deep, their surface testimonies folded, melted, or eroded. The net effect is a partial memory. Some breaths are well preserved, others are lost to the reflux of plate tectonics. For anyone searching for ephemeral traces of a brief surface perturbation, natural or technogenic, the tectonic theater imposes a filter that favors global scale, chemically disruptive events if any long-term signature is to endure. The interplay between volcanoes and the carbon cycle is a particularly consequential thread. Volcanic carbon emissions operate on timescales of millions of years and are normally balanced by silicate weathering. Uplift exposes fresh rock. Weathering draws down CO2. Rivers ferry bicarbonate to the sea, and carbonate sediments lock carbon away. But when volcanic outgassing outpaces weathering during intense magmatic episodes or rapid lip emplacement, the balance tips. Atmospheric CO2 rises, climate warms, ocean circulation can reorganize, and oxygen levels may fall as anoxia spreads in warming seas. Conversely, abrupt stratospheric sulfate injection can cool the planet, briefly increasing ice cover and altering weathering rates. Thus, the planet's strong breaths are not mere exhalations, they are forcings that can tilt the long-term respiratory balance of the world. If the narrator pauses for a concluding reflection, it is to note how tightly those strong, tectonically driven breaths reattach the small rhythms of life to the slow machinery of the planet. The diurnal opening of leaves, the seasonal ebb and flow of monsoons, the migrations keyed to predictable climate windows, all can be modulated, shortened, or temporarily suppressed by a volcanic exhalation or a seismic convulsion. At the same time, these breaths renew soils, create habitats, and modulate climate in ways that may sustain life over geological spans. The moral posture appropriate here is neither fatalism nor triumphalism, but a calibrated humility, to recognize that human projects are fragile when set against eruptions that can darken skies or flood continents with basalt, yet also to appreciate that those same processes have been central to the creation of the very conditions that made life and human culture possible. The final image is not of lava pouring or of ash settling, but of listening. The planet's strong breaths announce themselves across frequencies, in the infrasonic push of a plume, in the high-frequency crack of an earthquake, in the chemical whispers of sulfur and carbon recorded in ice. Instruments can hear them, cultures interpret them, ecosystems respond. To live wisely is to learn to hear these breaths, to recognize their force, to measure their chemistry, to understand their likely outcomes, and to shape civilizational responses that reduce vulnerability while respecting the tectonic theater that is part of the Earth's anatomy. The question that opens the next act is therefore simple and pressing. When the world pants and pants again, what will the consequences be for the fragile daily rhythms that have learned, over millennia, to rely on the planet's gentler cadence? What determines whether life flourishes like a green continent or collapses into silence? It is not a single gene or a single comet. It is the composition of the air itself, the balance of oxygen and carbon, the whispers of methane and the heavy persistence of carbon dioxide, and the rhythms by which those gases are moved, stored, and released. The planet's breath, in this sense, is a gatekeeper. When it deepens and clears, life explodes into novelty. When it thickens and chokes, life contracts and dies back. The question is not merely poetic, it is the mechanism by which biodiversity and collapse are written into the rock record. An increase in oxygen is the most straightforward access for biological exuberance. Oxygen is not just a gas, it is a multiplier of metabolic possibility. Where oxygen partial pressure rises, aerobic metabolisms gain energy efficiency by orders of magnitude compared to anaerobic pathways. Cellular processes speed up, multicellularity becomes less energetically costly, and the architecture of bodies can change. In deep time, the gradual rise of oxygen allowed aerobic respiration to support larger cells, more complex tissues, and the high energy demands of nervous systems. The Great Oxygenation Event and the later Neoproterozoic Cambrian oxygenation pulses set the stage for evolutionary radiations. In each case, a planetary exhalation of free oxygen translated into a flowering of anatomical experimentation. But that flowering carries its own counterpoints. As oxygen accumulates, it also alters fire regimes. Higher oxygen concentrations increase flammability. Leaf litter that would smolder under low O2 becomes kindling under high O2. Fire becomes not only ecological disturbance, but a powerful sculptor of landscapes, cycling nutrients quickly and favoring fire-adapted ecologies. Insects and other animals, sensitive to oxygen diffusion limits, may grow larger where oxygen is readily available. The fossil record hints at gigantism in certain intervals coinciding with elevated oxygen. Oxygen, therefore, is both a creative and a demanding agent. It opens possibilities for complexity while changing the selective pressures that determine which forms will survive. Oxygen's increase also interacts with the carbon cycle in profound ways. Photosynthetic productivity that drives oxygenation depends upon the availability of nutrients and on the burial of organic carbon. When organic matter is buried and not respired, oxygen accumulates because the carbon that would otherwise recombine with oxygen is removed from immediate circulation. Episodes of elevated organic burial can therefore amplify atmospheric oxygen, and those episodes are often tied to shifts in ocean circulation, redox structure, and continental configurations. The biological bloom is therefore entwined with geology, seas that stratify and sequester organic matter, deltas that trap sediments rich with plant debris, and tectonic uplift that exposes fresh rock for weathering, all modulate how oxygen accumulates or is consumed. In contrast stands carbon dioxide, a subtle and long-lived throttle of climate. Too much CO2, and the planet moves into a greenhouse mood, seas warm, ice retreats, and the chemistry of seawater shifts toward acidity. Ocean acidification, the result of CO2 dissolving and forming carbonic acid, dissolves the very skeletons that many marine organisms build from carbonate ions. Reef systems, the rainforests of the marine realm, are particularly vulnerable. When carbonate saturation falls, corals, foraminifera, and calcifying plankton struggle to maintain shells. Their decline restructures food webs, reduces biological carbonate export to the deep sea, and can lead to a cascade of extinctions. In the same breath, warming promotes stratification of the water column. Surface waters warm and become buoyant, inhibiting the mixing that would ventilate the deep ocean. Reduced oxygen solubility, combined with less mixing, yields expanding oxygen minimum zones and coastal dead zones. These chemical trajectories have been writ large in Earth's crises. The end. Permian extinction, long blamed on massive volcanic outgassing associated with large igneous provinces, is a case study in how greenhouse exhalations can suffocate the biosphere. Volcanic CO2 warmed the world. Warming led to changes in ocean circulation and oxygen content. Anoxia and euxinia spread across. Shelves, many marine clades collapsed under oxygen stress and acidification. Similarly, the Paleocene, Eocene thermal maximum, a relatively rapid injection of carbon into the system, produced a burst of warming, a reorganization of marine communities, and a reshuffling of terrestrial biomes. In each scenario, excess carbon did not merely heat, it rewired the chemistry and the breathing patterns of the planet. Between these two poles, oxygen-rich exuberance and CO2-driven suffocation, sits a complex tapestry of feedbacks. Methane is a swift, volatile actor, potent while present, but short-lived in the atmosphere relative to CO2. When methane oxidizes in an oxygenated atmosphere, it produces CO2 and water in low-oxygen worlds. Methane can accumulate and support a stronger greenhouse, ameliorating a faint young sun. But the transition from methane-dominated to oxygen-dominated atmospheres can itself be destabilizing. Oxidation of methane can produce cooling steps which, if combined with other forcings, may seed glaciations. In other words, the planet's breath is rarely steady, it shifts compositionally, and each component carries different radiative and ecological consequences. A less obvious but equally potent mechanism by which the breath becomes abnormal is subsidence, the sinking of land and seafloor that changes how the planet inhales and exhales. Basin formation, delta compaction, tectonic downwarping, and human-driven groundwater withdrawal all create regions where the chest seems to fall inward, altering the ventilation of sediments and the exchange between ocean and atmosphere. When shelves subside and basins deepen, organic rich sediments can accumulate under low oxygen conditions. These isolated pockets become incubators for methane and other reduced gases trapped beneath impermeable caps. If that seal is breached by warming, by tectonic uplift, by slumping of sediments, a sudden abnormal exhalation can occur. Methane-rich bubbles rising, puncturing surface waters, and spiking atmospheric greenhouse forcing impulses. Subsidence also reshapes coastal breathing patterns in ways that have immediate biological consequence. Deltas, where rivers meet sea, are natural lungs of the planet, high-productivity zones that exchange nutrients and carbon vigorously. When deltas sink, they concentrate sediments and organic matter in restricted basins. Nutrient trapping and restricted circulation combined can encourage eutrophication, blooms of photosynthetic organisms that die and sink, fueling microbial respiration and oxygen depletion. The result is widespread hypoxia and the formation of black shales in the sedimentary record. These hiatuses of oxygen are the geological signatures of a breathing gone awry, local pockets of suffocation that, when extensive, contribute to global biogeochemical shifts. Human influence exacerbates these subsidence-related pathologies. Extraction of groundwater and hydrocarbons, the engineering of rivers and coasts, and the loading of deltaic sediments with agriculture and infrastructure accelerate settling. The effective chest of a region compresses, wetlands are lost, and the buffering capacity of coastal zones erodes. When these human-induced changes intersect with warming seas and rising storm surge, the abnormal breathing becomes both acute and chronic. Reduced resilience to hypoxia, increased methane release from thawing permafrost and collapsing subsea permafrost, and more frequent pulses of toxic sulfide events. The planet's respiration acquires a new irregularity, one that human societies both amplify and must contend with. Biological responses to these shifts are varied and sometimes unexpected. Elevated oxygen favors organisms that exploit high-energy metabolisms. Oxygen spikes have been associated with episodes of body plan diversification. Conversely, the oxygenation favors those lineages able to tolerate low oxygen niches, anaerobic bacteria, certain invertebrates, and organisms capable of vertical migration to escape hypoxic layers. Mass extinctions often, therefore, rearrange the tree of life rather than simply prune its tips. The survivors are not the most complex necessarily, but those whose physiologies, behaviors, or life histories can negotiate the new breath. An additional consequence of abnormal breathing is the alteration of nutrient cycles. Widespread anoxia changes the fate of bioavailable nitrogen and phosphorus. Fixed nitrogen can be lost through denitrification, lowering primary productivity over time in some basins. Iron and manganese cycles are remade under reducing conditions. Trace metals that are toxic in oxidized forms may accumulate and poison life at thresholds. The net effect is a reconfiguration of food web-based productivity, altering energy flow from plankton to fish to larger predators. Fisheries collapse where oxygen is lost. Microbial blooms dominate where nutrients accumulate. These are not sterile chemical changes, but reweavings of ecological tapestry. From a stratigraphic perspective, abnormal breaths are legible. The sedimentary record preserves telltale markers. Black shales rich in organic carbon indicate widespread anoxia. Sulfur isotope excursions hint at shifts in sulfur cycling, and degrees of euxinia, enrichments in redox-sensitive trace metals like molybdenum or uranium, betray oxygen-poor bottom waters. Abrupt shifts in carbon isotopes mark rapid injections of isotopically light carbon, as with methane bursts. Charcoal layers signal intervals of enhanced fire activity tied to high oxygen. These proxies are the planet's own stenographers, capturing the narrative of breaths that either nurtured or suffocated life. There is a moral and existential quality to this geology. The same mechanisms that allow life to succeed on geological timescales, efficient burial of organic matter, the weathering of rocks, the sequestration of carbon in carbonate shells, can be subverted by rapid perturbation to produce collapse. A system that breathes with patience can be made to hyperventilate by forcings that outpace its stabilizing feedbacks. The planet's capacity to absorb greenhouse gases through weathering and sedimentation exists, but it operates at tempos that are often glacial relative to the urgency of rapid emissions. What follows is a mismatch. Human-scale impulses applied to geologic systems yield pathologies visible not only in climate graphs, but in the silent black layers of sediment that will be read by future geologists. Speculation about long-vanished technogenic disturbances must contend with these same biases. A civilization that perturbed carbon cycling briefly might leave a chemical fingerprint, a pulse of unusual isotopes, an anomaly in redox-sensitive elements, or an abrupt change in sedimentary assemblages. But if those perturbations did not alter basin mechanics or cause extensive burial of novel compounds in durable strata, the memory may be smudged by the planet's habit of recycling its surface. Subsidence, ironically, can both preserve and erase. It can bury a technogenic signal quickly into anoxic sediments where it is protected from oxidation. Yet later, tectonic uplift or metamorphism can destroy that record. Detection requires that an anomalous breath be large enough to push the planet into a state that the sedimentary record preferentially archives. There is also the human-scale sensation of these dynamics, an emotional accounting that alternates between awe and dread. To imagine oxygen as a promoter of complexity is to feel wonder at the processes that allowed multicellular life to flourish. To imagine CO2 as an agent of suffocation is to feel acute vulnerability. Subsidence adds a mechanical unease. The land itself can collapse like a lung deflating, sediments settling into new geometries that trap gases and reroute currents. The emotional tenor is not merely poetic, it is pragmatic. Societies have historically been attuned to riverine and coastal breathing patterns, the rhythms of flooding, the pulse of monsoons, the seasonal bounty of fisheries, and they are acutely sensitive to their disruption. When the planet's breath changes rhythm or composition, cultures are forced to adapt or vanish. The final, pressing realization is that the planetary respiratory system is a web of interdependencies. Oxygen, carbon, methane, water, and the physical architecture of shells and mountains do not operate in isolation. They compound one another's effects, sometimes buffering, sometimes amplifying. The paleo record is a library of experiments in which the planet tried different breathing modes and recorded the winners and losers. Those records are not recipes, but cautionary tales. Oxygen enrichment can be generative, carbon excess can be lethal, subsidence can create pockets of suffocation or traps of preservation. The modern era adds a new variable, a species capable of altering the composition and tempo of the breath on decadal timescales. To read these patterns is to inherit responsibility as well as knowledge. Instruments, satellites, sediment cores, isotope laboratories can translate the planet's breath into actionable understanding. Yet the narrative finality resides not in measurement alone, but in choice, whether to allow the respiratory system to be forced into abnormal, potentially irreversible patterns, or to act in ways that respect the deep time rhythms that have, thus far, made life possible. The breath of Earth determines whether habitats expand or contract, whether new ecologies are carved out of opportunity or erased by suffocation. In the interplay between oxygen's promise and carbon's peril, under the shadow of subsidence that can make lungs stutter and fail, lies the fundamental biological and climatic consequence, a living world that is as delicate in its chemistry as it is immense in its time. Can humanity mourn what it cannot see? That is the opening question, not a scenic picture, but a small, insistent problem. People stand on a narrow ledge of time and attempt to interpret the slow breathing of a world whose lungs operate in rhythms far longer than a lifetime. Instruments listen for a handful of exhalations. Instruments hand back graphs and numbers and images. From those few breaths, a story must be reconstructed. The philosophical weight of that act, the act of translating brief, instrumented gasps into judgments about loss, continuity, and responsibility, is what this chapter takes into the light. The practical truth is stark. Human direct perception samples only a slender band of the planet's respiration. A single human life can watch sea level rise by centimeters, see a coral reef bleach, record a year with exceptional storms. Instruments extend perception. Satellites map the color of oceans and the thickness of ice. Ice cores trap air bubbles and stack. Then, like beads of time, tree rings count wet and dry seasons. Ocean sediment cores accumulate slivers of phytoplankton and dust. But collectively, these records represent only a handful of breaths when set against Milankovitch cycles, glacial, interglacial oscillations, and tectonic timescales. To stand amid this mismatch, brief instruments' patient planet is to face the limits of knowing. Instruments themselves are worth a long, close look. Consider the drill rig over an Antarctic ice sheet, a metallurgical throat that cuts into snowfall compacted for millennia. It hums, a mechanical insect, the sound of engines and hydraulic pumps under a crystalline sky. Snow, compacted into layers, is plucked out like a ribbon and brought indoors. In the lab, a thin slice is shaved and examined under a microscope. Air bubbles are extracted and run through a mass spectrometer. That produces peaks and shoulders, the fingerprints of ancient atmospheres. Each spike on those readouts is a breath recalled, a winter of ash-laden skies, a year of elevated methane, a volcanic veil. The emotional register in that room is particular, a mixture of reverence for the fidelity of the archive and a tightness that comes from realizing how little of the record can be directly read from any single core. The archive is rich but fragmentary. Its completeness is an illusion at a scale convenient to humans, and an outright impossibility at the scale of deep time. Or consider satellite records, the long line of missions that have watched Earth from high orbit. The imagery is immediate and intoxicating. The Fourier hum of sea surface temperature anomalies, the shifting eddies of chlorophyll concentration, the seasonal wax and wane of snow and ice. Its satellites barely celebrate half a century of continuous observation for many variables. For greenhouse gases, the modern atmospheric observing network is barely over 60 years deep. That is a handful of planetary breaths. The problem is not merely length, but sampling frequency and aliasing. Put simply, to infer a slow oscillation reliably, one must sample it adequately. If one listens to a single inhale and then separates the listener for decades, the reconstructed pattern risks being a hypothesis stitched from noise. A Nyquist-like problem in time series perception to reconstruct slow rhythms from fast, sparse sampling is a technical constraint with philosophical implications. A truncated record is vulnerable to false narratives. Those vulnerabilities are compounded by signal transformation and the process of proxy measurement. An ice core measurement does not record atmospheric composition, as it was in the thin instant of a season. It records a compressed, filtered, chemically altered signature. Trees do not record global oceanic oxygenation. They hold local moisture and temperature signals. Marine sediments record biological productivity modulated by currents, nutrient availability, and post-depositional chemistry. Each proxy is a transformed echo, a convolution of many processes. To interpret these echoes, a scientist constructs models, mechanistic and statistical, that untangle probable causes. That modeling is an act of translation, converting a chemical ratio, an ink-dark band in mud, or satellite radiance into narrative statements about the breath. It requires assumptions, priors, and a willingness to accept uncertainty. The honest emotional response to this effort is humility, an acknowledgement that clarity is rarely total. There is also an archival asymmetry that has moral resonance. Some changes are easily preserved, others are fragile. Ice cores and varved sediments can preserve atmospheric signatures with exquisite resolution for tens to hundreds of thousands of years. In such cases, a spike in sulfate or a particular isotopic ratio can tell a precise story. But the very things humans worry about, the architectures of cities, the ephemeral plastic of street life, the day-to-day arrangements of societies, are poor candidates for durable geological memory. Stone may survive, but most other materials are vulnerable to erosion, burial, and chemical transformation. A civilization that flared and faded on a time scale of a few centuries may leave a thin chemical smear in deep time, but its cultural particulars will almost certainly be lost. The planet records chemistry far more faithfully than culture. This differential preservation forces a particular kind of grief, the loss of social knowledge, and the extinction of contexts that cannot be directly recovered. There is a parallel intellectual loss, an inability to perceive the approach of thresholds in time to act. Human senses and institutions are poor approximations of anticipatory mechanisms for long-term processes. A lake that slowly oxygenates over decades will escape immediate notice until a tipping point is crossed and a collapse occurs within years. A permafrost layer that maintains a frozen integrity for centuries can thaw in accelerated pulses once a threshold is crossed, releasing methane in a burst that instruments might register only after the process has begun. The catastrophe, when it arrives, is not always abrupt geologically, but relative to human planning horizons it can be sudden and decisive. That latency, the lag between cause and readable effect, is ethically crucial. It explains a distinctive posture of modern environmental philosophy, that stewardship must be exercised under conditions of deep uncertainty. Perception itself is shaped by culture and cognition. Humans suffer a shifting baseline problem. Each generation inherits a version of normal that is already altered by previous losses. Ocean biodiversity assessments compiled across centuries show this effect clearly. A fish population that seems abundant to a 19th century observer may appear depleted to a 21st century one. Both are interpreting different baselines as normative. This cognitive narrowing makes grief peculiar. It is often partial, fragmented, and delayed. Loss is cumulative, yet mediated by narrative memory, and narrative memory can be rewritten. The philosophical consequence is disquieting. A lot of damage is quietly normalized, folded into the new ordinary, until only the geologist's archive can point to the gradual erasure beneath a sense of continuity. Even when instruments register change, the next step, comprehension, is not automatic. The mass of data, its heterogeneity, the need for long-term continuity in observation, and the overlay of human political and economic priorities complicate interpretation. Consider a decade of elevated ocean heat content. Satellites and floats may show an unequivocal trend, yet translating that into societal advice. Fishery closures, coastal adaptation, migration assistance requires institutions capable of working on timescales beyond an electoral cycle. The philosophical tension appears here as well. Knowledge exceeds the human capacity to act coherently on long-term risks, and that failure amplifies the emotional load placed on those who perceive. If the planet's breath is a polyphony of timescales, loss and mourning must be rethought in polytemporal terms. Grief is not merely for the species that vanish in a single summer, it is for the slow diminution of ecological potentials, the loss of a wetland's sequestration capacity, the gradual erosion of soil depth that underpins agriculture, the attrition of genetic diversity over centuries of selective pressure. These are losses that instrumentation can partially quantify, but that are felt culturally only rarely and then often too late. The philosophy of loss must expand to include delayed accounting, a ledger that recognizes not just immediate deaths, but the lost resilience that earlier stewardship might have preserved. There is an ethical slope to the limitations of perception. When only a few breaths are measurable, decisions are made under a veil. The choice to build a dam, to clear a forest, to change a river's course, or to mine peat involves projecting uncertain long-term consequences from short-term data. The moral question is about responsibility for the unseen. It is one thing to act with known immediate effect. It is another to alter a slow rhythm that will be read by future instruments, long after the actors have gone. That moral horizon, stewardship for those who cannot yet measure the world's full breadth, is intangible but necessary. Practical resolutions exist, but they require reconfiguring institutions and attention, extending continuous observation networks, supporting long-term archives that do not depend on ephemeral funding cycles, investing in paleosciences that translate deep signals into actionable insights. All these are technical answers. The deeper remedy is cultural, cultivating a public ethos that values long-term thinking and collective memory. It is the difference between treating instruments as curious gadgets and treating them as the planetary stethoscopes of a civilization. Yet even the best instruments are only as meaningful as the stories told about their output. Data without narrative confers little obligation. Narrative without data risks being sentimental. The marriage of careful measurement and thoughtful interpretation must be the foundation of any ethic of loss. There is an additional layer of humility in the face of erasure. The planet sometimes protects and sometimes obliterates evidence. The same ocean currents and sedimentary basins that can fold an atmospheric perturbation into a chemical layer also dilute and disperse localized signals. Tectonic recycling can later obliterate whole chapters of surface history. Therefore, the absence of a readable trace in the deep archive is not evidence of absence of past perturbation. That epistemic modesty is philosophically important. It forbids certain lines of smug certainty, the temptation to declare that nothing of consequence has ever changed because the archive appears silent. Silence in the geological record is noisy with ambiguity. The emotional labor of living with these limits is complex. There is bereavement for the species and landscapes visibly lost. There is a quieter, more pervasive melancholy about the irretrievability of context that shaped human meaning. At the same time, there is a countervailing awe. Instruments reveal a planet of unfathomable patience and resilience, one that erases some crises and records others, one that has survived radical chemical rearrangements and yet preserves a capacity for life. That duality, grief alongside a sense of participation in something larger, should not devolve into fatalism. Instead, it can motivate a different kind of agency, careful, cautious, directed towards maintaining the conditions for continuity. Finally comes the practical, speculative question that frames the chapter: can humans, with instruments that have recorded only a handful of breaths, come to understand the long rhythm sufficiently to act with prudence? The answer is partial. Scientific methods give pathways, multi-proxy synthesis, ensembles of models that explore uncertainties, long-term observatory networks, and cultural investment in institutional memory. Philosophically, the answer is temperamentary. Cultivate epistemic humility, embrace intergenerational responsibility, and accept that perfect knowledge will remain forever out of reach. The moral posture required is not paralysis but prudent action under uncertainty, hedging against catastrophic thresholds, restoring redundancy in ecosystems, and building social systems capable of responding to surprises revealed by the few breaths. Science can measure. The chapter closes, obedient to its initial call to question rather than to spectacle, with another question that leans forward like a listening posture. If humanity can hear only a few breaths of the earth, will that partial hearing be enough to inform a stewardship worthy of what is being lost? The answer will not be immediate. It will be written in the patience of institutions, in the courage of cultures to mourn slowly, and in the fidelity of instruments that will continue to listen when individual lives have ended. The long rhythm remains inscrutable in parts, but its ethical demands, to notice, to preserve, to act with humility, are immediate. What if a single lifetime were measured against the patient lungs of the planet? The question is less a curiosity than an ethical prism. When a species with the brief attention span of a century reaches into a system that breathes in million-year cadences, what does its intervention look like? Does a century count as an instant in a ledger of rocks, or can an intense, concentrated century leave fingerprints that the slow pulsing of geology will be forced to read? Part 10. Current connections. Climate change today is not simply a change statistic on a graph. It is a respiratory disorder, writ planetary. To take that image seriously is to translate clinical metaphors into global processes. The baseline composition of the atmosphere, the ratio of oxygen to nitrogen to trace gases and greenhouse components, is the steady-state chemistry that keeps metabolism possible, the mix against which life arranges itself. Industrial emissions are not benign additions to that mix. They are foreign bodies particulates and molecules introduced into fragile airways, altering viscosity, clogging capillaries of sunlight, changing exchange rates between atmosphere and ocean. In clinical terms, the planet's breath shows both obstructive and restrictive pathologies. Airflow is impeded where aerosols and particulates block radiative equilibrium. The capacity to expand and cool is limited where heat is trapped by excess greenhouse gases. The modern industrial epoch is a dramatic spike on a very long curve. CO2 concentrations, stable for millennia within a range that helps sustain the Holocene, have risen steeply in a single blink of geologic time. Methane, nitrous oxide, aerosols, and a cocktail of synthetic compounds now circulate in the lower atmosphere where once the chemistry had only subtle, natural variation. This is a forced exhalation of compounds that the system had not evolved to receive at this rate. The result is both immediate discomfort, heat waves, extreme storms, droughts, and a long-term recalibration of baseline conditions, altered precipitation regimes, shifted biome boundaries, ocean warming, and acidification. To call it a breathing disorder is more than poetic. The lungs of Earth, forests, wetlands, phytoplankton, soils have been compromised and overloaded. Deforestation is a loss of alveolar surface area, drained peatlands are an exhalation of stored carbon, ocean heat uptake is a redistribution of thermal burden into the deep where it changes stratification and cuts off ventilation. Pollution, particulate matter, black carbon, darkens reflective surfaces and accelerates melt where snow and ice are present. Industrial aerosols can even mask some warming regionally by reflecting sunlight, producing a cruel ambivalence. The very particles that degrade local air quality and harm health also produce a temporary, uneven cooling, acting as a bandage that hides the underlying metabolic imbalance. The planetary analog to pulmonary inflammation is visible in the feedbacks that amplify warming. Thawing permafrost releases methane and CO2 like pockets of trapped gas released when tissue breaks down. Massive diebacks of forests or the collapse of coral reef systems reduce the planet's capacity for gas exchange. These are positive feedbacks, processes that, once triggered, accelerate the disorder of respiration. They are the biological cascades that convert a metabolic hiccup into a chronic disease. The clinical image holds up in surprising detail. Some disturbances resemble acute, sharp breaths, volcanic eruptions, wildfires, sudden episodes that change aerosol loading and temporarily alter climate. Others are chronic. The slow, steady buildup of CO2 resembles long-term scarring. A fibrotic stiffening that reduces the amplitude of normal seasonal breathing. Anthropogenic emissions are not only chemical insults, they are mechanical alterations of circulation. Cities with heat islands and reduced vegetation alter local convective patterns. Large dams and irrigation projects rewire the hydrological system, changing the transport of moisture and the timing of inhalations and exhalations in regional climates. There is a social dimension to this pathology. Just as lung disease does not strike societies uniformly, neither does climate harm distribute evenly across the globe. Vulnerability is a function of exposure and capacity, where people live relative to coasts and river basins, their ability to adapt, and the legacies of inequality that shape resource access. The same pollution that cools certain regions through aerosol shading tends to harm those who produce or live near the emissions, and the storms that intensify with a warmer atmosphere disproportionately batter the least resilient communities. Ethical assessment cannot be separated from the physiology. Who breathes the worst air, who suffers the immediate consequences, and who benefits economically from the systems that alter the breath? There are instruments that act like stethoscopes. Satellites read heat and albedo, ocean floats measure warming at depth, aerosol networks track particulate plumes, ice cores trap millennia of air in crystalline bubbles. Together they convert sensation into measurable data, respiratory rates of CO2, methane, nitrous oxide, changes in seasonal CO2 amplitude, shifts in heat content stored in oceans. The data translate to diagnosis. The system's tidal balance is shifting toward a new respiratory baseline, and some components are failing to respond on the necessary time scale. But the clinical measurement does not automatically translate into treatment. The anatomy is clear. The social, economic, and political means to direct change are less decisive. What does treatment look like? Medical analogies are imperfect but suggestive. If the planet's lungs are clogged by smoke, soot, and excess gas, therapy involves both removing the obstruction and restoring healthy tissue. On the removal side, emissions reductions, the phasing out of fossil fuels, the curtailment of practices that produce potent greenhouse gases. These are immediate steps that reduce the burden of foreign bodies in the airway on restoration, reforestation, peatland rewetting, regenerative agriculture, ocean stewardship, and investments in carbon dioxide removal are attempts to return surface physiology to a more functional state. But restoration moves at geological paces. Regrowing an ecosystem or rebuilding soil carbon can take decades to centuries. The mismatch between urgent need and long-term response frames a central ethical challenge: how to prioritize interventions under temporal constraints and how to allocate burdens and benefits across unevenly resourced societies. There are also iatrogenic risks, interventions with unintended consequences. Geoengineering proposals, from stratospheric aerosol injection to large-scale carbon capture, carry risks that mirror the ambivalence of medical treatments with side effects. Injecting aerosols might mask warming but could disrupt precipitation patterns and create political dependencies. Large-scale carbon removal must be carefully managed so as not to reduce biodiversity or siphon resources from equitable adaptation. The planetary system is complex. Interventions often ripple in unexpected ways. Human perception complicates the clinical picture. Short attention spans and economic short-termism mirror a clinical impatience for quick fixes. The temporal compression of politics, election cycles, market quarters is a poor match for therapy that requires multi-generational commitment. The challenge is partly technological and partly cultural: how to build institutions that value long-term respiratory health for a planet whose lungs are both diffuse and shared. That task requires a reorientation, seeing climate and biosphere stewardship not as optional policy lines, but as primary infrastructure for continued civilization. There is a metaphysical sting in the image of industrial emissions as foreign bodies. The metaphor suggests violation, an organ invaded by alien material. It captures a moral intuition that species with reflective capacities bear responsibility in a way that other agents do not. The planet itself has no moral calculus. It responds to forcings according to physics and chemistry. But humans, who can foresee and model consequences, occupy a different category. The medical analogy becomes prescriptive, not because the Earth is a patient in need of moral counsel, but because humans must decide whether to act as doctors, carers, or indifferent observers. The question persists then, about timescales. Can a century of industrial activity produce durable scars that geology will read? The answer is mixed. Some signals are ephemeral in the atmospheric sense, yet durable in geological archives. The rapid rise in carbon dioxide and the isotopic signature of fossil fuel carbon, the Suez effect, is already a clear global marker. Nuclear activities have left technogenic isotopes in sediments and ice. Plastics, microplastics, and certain synthetic molecules, when buried in sediments, can persist for very long times. Conversely, cities, roads, and most surface infrastructure are ephemeral on million-year timescales. Tectonics buries, erases, and recycles. The planet removes many traces with patient efficiency, but certain chemical and isotopic anomalies are likely to outlast civilizations as readable scars. That possibility puts the present into sharper ethical relief. If 100 years of concentrated industrial force can imprint a detectable signature for eons, then the time horizon for responsibility extends beyond immediate human memory. The breath of the earth may be patient, but it also archives selective episodes. That archival selectivity is itself an ethical constraint. The practices that alter global chemistry, the most dramatically, are those that write most clearly into the long-term record. The question of legacy, what will future geological readers infer from the strata we leave behind, becomes an argument for prudence. Part 11. Check. If the planet's timescale is the sea on which human projects are launched, then there is an unspoken translation problem: how to transpose ethical urgency from a century into a story written in millions of years. The shorthand that millions of years equal a mere 100-year human life is both true and deceptive. Human lifetimes are infinitesimal against deep time, yet intensity matters. A concentrated set of actions within a single century can force the planetary respiratory rhythm into a different mode for millennia. The question implicit in millions of years equal 100 years is not a mathematical curiosity but an inquiry into causation and legacy. What does concentrated agency do when applied to a slow, reactive system? The answer is contained in the mechanics of buffers and thresholds. The Earth's respiration includes fast components, daily photosynthetic draws, seasonal monsoons, and slow ones, silicate weathering, plate tectonics. Disturbances that leave the slow components untouched can be transient. The system's buffers absorb the shock and re-equilibrate. Disturbances that push the system beyond thresholds, forcing new equilibria in carbon storage or oxygenation, can endure. An intense methane pulse or a sustained CO2 increase can change ocean chemistry, foster anoxia, and create sedimentary layers rich in organic carbon that will be read in the rock record. Those changes are not simply temporary noise, they can be geological events. Thus a century is not necessarily insignificant. A rapid perturbation can catalyze processes that operate on geological timescales. Think of it as inducing an arrhythmia in a heart that then entrains a new rhythm. The initial perturbation is brief, the aftermath is prolonged. That fragility is both technical and ethical. From a scientific standpoint, understanding which perturbations are likely to trigger durable changes is a pressing task. It requires integrating climate science, oceanography, geomorphology, and biogeochemistry into models that can trace short-term forcings into long-term consequences. From an ethical standpoint, it requires accepting that actions today are not merely proximate choices, but potential geological authorship. The responsibility that follows is twofold. First, mitigation. Reduce the rate and magnitude of perturbation so the system's inherent buffers can keep functioning. Second, care for the system's record-keeping organs, protect wetlands, maintain soils, preserve coral reefs and seagrass meadows that both stabilize carbon and hold biological memory. These are not merely preservationist platitudes. They are operational measures that reduce the chance of pushing the system past thresholds where a century writes a million-year sentence. There is an imaginative calibration needed as well. Most cultures are wired to immediate hazards and immediate rewards. The human psyche, shaped by survival in fluctuating environments, prizes rapid feedback. Deep time thinking, by contrast, asks for a radical expansion of moral imagination, stewardship for the many generations that live beyond the horizon of political calculation. It asks institutions to judge projects not merely by their short-term returns, but by their planetary legacies. Practically, building such institutions involves new forms of accounting. Climate policy needs to internalize the longevity of certain emissions into present-day costs. Infrastructure planning must incorporate potential long-term changes in sea level and sedimentation regimes. Economic systems must find ways to value long-term ecosystem services that are currently treated as externalities. These are political and economic challenges, not purely scientific ones. The science provides the diagnosis. The polity must choose to follow the better prognosis. There is a final existential note to this translation. The recognition that a century can equal a million-year signature calls for a humility that is difficult to sustain. It asks our policy be guided by precaution, by a willingness to forgo certain conveniences because the apparent benefits are outweighed by the long-term costs. It calls for narrative change, stories, rituals, and cultural commitments that reframe prosperity as longevity of habitability rather than the accumulation of ephemeral goods. This is not a call to ascendancy or asceticism, but to proportionality. The planet will continue to breathe in rhythms that far exceed human lifespans. Yet, it will also read some human breaths as meaningful inscriptions. To live well in such a world requires a double awareness, the smallness of a single life and the potential potency of collective action. If the choice is to congest the lungs of the planet with foreign bodies for the sake of short-lived gain, then geology will remember. If instead the choice is to tend, to remove obstructions, and to nurse the planet's exchange surfaces back toward healthier functioning, then that too will be recorded, not only in the rocks but in the continuance of a biosphere that can host the intricate cultures that make moral reflection possible. In the end, the arithmetic of time is not only about adding zeros. A million-year process does not simply swallow 100-year one, it can be altered by it. That is the paradox that sits at the heart of responsibility. Human lives are brief, but they are not inert. Their concentrated agency can nudge planetary breathing toward new baselines. The pressing question becomes ethical rather than technical. What kind of breath will the present choose to imprint upon deep time? And what stewardship practices will be adopted in recognition that the lungs of the earth, once clogged or scarred, take long, patient labor to heal? What if the world simply stopped breathing for a day? It is a question that reads like a prompt for science fiction, but it is, more usefully, A thought experiment about rates and resilience, about what happens when processes that normally trade heat, gases, and moisture across the surface pause long enough for consequences to be felt. The imagination here need not invent miracles. It need only attend to the ordinary mechanics of exchange and then ask what there. Temporary suspension would reveal. In that suspension, the planet's usual modesty is stripped away, exposing which processes are fragile and which are patient. The answer is both less catastrophic and more instructive than a melodramatic collapse. A single-day stoppage would be survivable for most life, yet it would also be an amplifier of local inequality and an uninvited demonstration of how tightly knit the biosphere's minute rhythms are to human societies begin at the scale of a city on a summer afternoon. A day without breath would first be noticed in the way air sits. Without the convective churn that comes from differential heating and wind redistribution, heat would pool near surfaces, the boundary layer would shallow, pollutants emitted from vehicles and industry would accumulate where they are released, rather than being diluted and advected away. The result is a dense, acrid air that stings eyes and constricts lungs, a localized suffocation measured in micrograms per cubic meter. Epidemiologists would expect spikes in respiratory distress. Hospitals would record an immediate, measurable uptick. For urban residents, the day would be heavy and smothering. For those living downwind of fires or volcanoes, the pause of transport would mean sharp, acute exposure. Those city-scale discomforts, however, are surface symptoms of deeper disruptions. Atmosphere and ocean exchange heat and gas not only by the dramatic gusts of storms, but by a constant background breathing. Diurnal convection, trade winds carrying moisture across continents, sea breezes that cool land at noon and return warmth at night. If those flows paused, coastal zones would experience a strange flattening. Sea breezes that ordinarily pull cool, humid air inland would not arrive. Coastal fogs might remain stuck over water rather than inshore. Inland, the soil would heat faster. Plants would close stomata earlier to conserve water as humidity fell in the near-surface layer. Photosynthetic uptake would slow in that thin, hot film of air. The initial chemical consequence of an arrested day is therefore not an immediate planetary CO2 spike, but a constellation of local chemical stresses that, aggregated, reveal how sensitive human and ecological systems are to continuous exchange. In the oceans, the picture is quieter but no less consequential. Surface mixing, driven by wind and turbulence, is a major mechanism by which the upper ocean exchanges oxygen and heat with deeper layers. A day without wind reduces surface mixing. The top layer would warm slightly faster under solar input and deoxygenation in. Localized microenvironments could accelerate where biological consumption is high. Plankton near the surface might experience intensified stratification, a warmer, nutrient-starved top layer over a colder, nutrient-rich subsurface. Phytoplankton, which depend on the upwelling of nutrients, could falter in productivity over those hours, with ripple effects on the immediate food web. For most marine systems, a single calm day is not fatal. For systems already on the edge, a hypoxic coastal lagoon, a coral reef stressed by warm seas, it could be the tipping point that triggers a bleaching event or a localized fish kill. Biogeochemical rhythms respond to the cessation of breath in sniffable ways. Urban air samples would show accumulation of volatile organic compounds and nitrogen oxides. Inland mountain stations would sense an odd absence of transported aerosols. Weather satellites would record a plateau in cloud movement and perhaps a temporary suppression of convective cloud formation where daytime heating is trapped near surfaces. Instrument arrays that track CO2 and methane would register only slight perturbations globally, because atmospheric mixing times are long and the planet's inventory of gases is enormous. But in the patchwork of local environments, the day would read as an experiment, air chemistry concentrated, moisture redistribution arrested, and the microclimates upon which agriculture depends momentarily unmoored. If the pause were psychologically revealing, it would expose the fragility of human systems adapted to continuous flow. Power grids reliant on predictable wind or hydropower would face short-term imbalances. Shipping and aviation might be delayed, not because of catastrophic storms, but because of unexpectedly still air and unusual surface temperatures. But the social consequence most instructive is the unequal distribution of impact. Wealthier infrastructure, filtered buildings, reliable medical services, air-conditioned spaces would blunt the day's effects, while vulnerable communities would bear disproportionate burdens. The thought experiment becomes a moral probe. A one-day stoppage is survivable in aggregate, but brutally discriminatory in effect. Now imagine the inverse, a world that breathes faster. faster breathing can be understood several ways. It might mean an accelerated hydrological cycle, more evaporation from warm surfaces, faster transport of moisture into the atmosphere, more intense and compact rainfall events. It might mean an accelerated carbon cycle, faster release of greenhouse gases from thawing permafrost, soils, and disturbed carbon reservoirs. It could mean faster biological turnover when warming stimulates metabolism. Or it might mean an increase in the amplitude of exchanges, stronger winds, more vigorous thermohaline adjustments, a quicker flushing of atmospheric constituents through convective storms. Each rendition leads to a different ensemble of impacts. But the common thread is an intensified pace of change that compresses responses and amplifies extremes. A faster hydrological breathing is perhaps the most intuitive and already observed symptom of warming. Warmer air holds more water vapor. When storms form, they deliver more precipitation in shorter bursts. The result is a paradox. Many places will be wetter in extremes, yet drier on average. Floods will overcome infrastructure designed for slower, predictable cycles. Crops timed to historical seasonal rains will be drowned or starved as moist seasons concentrate into violent episodes. River systems will recalibrate. Flash floods will punctuate long dry spells. Sediment transport will spike during pulses, and deltas will be alternately starved and inundated. Urban stormwater systems, engineered for older tempos, will fail more often, leading to cascading infrastructure breakdowns. Faster carbon breathing is more insidious. Permafrost soils have for millennia stored carbon and methane under frozen lock. As the planet warms, thaw fronts migrate, microbial activity accelerates, and gases are released. If these releases occur in a pulse, a rapid exhalation of methane and CO2, the greenhouse forcing intensifies at rates that outpace the capacity of sinks like the deep ocean and weathering to respond. The ocean, absorbing heat faster, stratifies. The biological pump weakens as nutrient recirculation slows, decreasing deep carbon sequestration. Oxygen content in the upper ocean drops in warm layers because warmer water holds less dissolved gas, and microbial respiration consumes more oxygen as metabolic rates rise. The outcome is a faster turning respiratory system that, through a dozen feedbacks, can push large regions into hypoxia and accelerate biological stress on a planetary scale. A faster wind-driven respiration reorganizes heat transport across latitudes. If jet streams and storm tracks shift because of altered temperature gradients between equator and pole, weather becomes less predictable and more extreme. Regions that once enjoyed regular seasonal variability will instead experience abrupt reorganizations of climate. Agricultural zones might migrate poleward faster than soils can develop, upsetting food security and prompting human migrations. Coastal systems, battered by more frequent intense storms, will see surge events that reshape shorelines and force expensive engineering responses. Faster breathing has another, less obvious effect. It compresses time for adaptation, biological evolution, cultural adaptation, infrastructure planning. Each operates on characteristic tempos. When environmental change accelerates, the window during which ecosystems and societies can adjust narrows. Keystone species with slow life histories, large trees, long-lived corals, animals with slow reproductive cycles are particularly vulnerable. Human institutions, preoccupied with shorter electoral cycles and market fluctuations, struggle to marshal the foresight and resources required for long-term resilience. The urgency created by a faster breath exposes mismatches between the rate of perturbation and the pace of societal response. Both the day-long pause and the accelerated breath converge on one stark lesson: the significance of rate. The planet's long-term buffers, silicate weathering, sedimentary sequestration, mantle storage operate on timescales of millennia to millions of years. They can and do repair and moderate, but they do so slowly. Rapid perturbations, even if brief in absolute time, can cascade into longer-lived changes by pushing systems past thresholds. A single abrupt pulse of greenhouse gas can drive ocean chemistry into states that favor widespread anoxia for centuries. A concentrated century of emissions can leave isotopic fingerprints read by geologists millions of years hence. The breath's tempo determines whether disturbances remain transient disturbances or imprint themselves upon the geological ledger. This is where the thought experiment becomes an ethical instrument. The notion of a day without breath, or a planet hyperventilating, is not simply hypothetical dramaturgy. It tests human assumptions about acceptable rates of change. If a single day of arrested exchange is survivable yet unequal, what moral imperative follows for averting longer, faster alterations? If rapid respiration amplifies danger by compressing adaptation time, Who bears responsibility for pacing the change? The answers do not lie in natural law alone. They require social commitment to reduce forcing and to bolster buffers that operate on longer timescales. There is, too, a diagnostic opportunity in these counterfactuals, a deliberate experiment of the kind that a day-long pause mimics inadvertently reveals sensitivity of systems under stress. Urban air quality responses expose vulnerabilities in public health infrastructure, coastal responses to stalled sea breezes, disclose dependencies on atmospheric circulation. Ocean surface responses show how close certain reefs or upwelling systems are to functional collapse. Watching how systems react to a cessation or acceleration of exchange would teach more about resilience, and a passive, gradual monitoring could. It is a harsh pedagogy, but it is instructive. The planet's breath is both signal and test. The documentary lens turns finally from diagnosis to agency. Humans cannot push a planetary pause button and expect the world to resume unchanged. They cannot compel a faster breath without consequences that echo. Yet the metaphor of a button is useful because it concentrates responsibility. Decisions made by societies to emit, to conserve, to restore are choices that alter rates of exchange. They are, in effect, the levers on a complex machine. Some levers are blunt, burning fossil carbon pumps CO2 into the atmosphere rapidly. Others are surgical, re-wetting peatlands, restoring mangroves. Changing agricultural soils can slow the release of carbon and enhance sequestration, restoring the planet's exchange surfaces and increasing resilience. The moral shape of that lever is not the same as the mechanical one. It requires an appreciation of thresholds and feedbacks, an investment in distributed, long-horizon institutions, and above all a willingness to accept constraints that prioritize the continuity of habitability over short-term gain. The planet's breath is not a commodity to be accelerated or decelerated for convenience. It is a condition of shared existence. To steward it demands humility, technical skill, and collective will. A final image, precise, deliberate, and small, offers it close to this section. Imagine an old coat, its fabric mended again and again along the seams where it has worn thin. The last stitch is never merely functional. It is a deliberate act of care, a choice to keep the coat whole for another season. In that sense, the world's respiratory system invites similar mending. Choices to reduce emission, to restore wetlands, to protect forests and soils are not spectacular acts of control. They are stitches, patient and persistent. They do not stop the wind or compel the ocean to be still, but they change how the fabric wears. There is no single emergency button that resets deep time processes. There is instead a succession of small, deliberate closures, policy decisions, conservation acts, the painstaking reweaving of degraded land that together fasten the future to a safer scene. The sound of the final button being fastened is small. It is quiet because what it accomplishes is not spectacle but maintenance, a deliberate fastening in the knowledge that the coat will be worn by many seasons yet to come. The planet's breath will continue, sometimes pausing in patterns humans cannot anticipate, sometimes quickening in ways that will demand ingenuity and sacrifice. The imperative is to choose the kinds of stitches that preserve exchange surfaces and avoid pushing the system into breaths that, once started, will be difficult to stop. The closing is thus not an act of finality but of continuity, a conscientious, modest fastening that recognizes the vast patience of Earth and the concentrated potency of human choice. What would it mean, finally, to answer the question that is threaded through the entire narrative? If the Earth breathes, how should the creatures in its lungs behave? That is not a pragmatic checklist alone. It is a philosophical challenge that asks who humans are in relation to a system that operates across scales far larger than any society's planning horizon. The question opens a set of ethical and practical implications as stark and urgent as any medical diagnosis. To listen, to adjust behavior, to become, in the aggregate, what a healthy alveolus would be: small, cooperative, adaptive, and attentive. The first recommendation is a posture of listening. Listening is not passive. It is a disciplined epistemic practice that combines tools and temperaments. The world has arrays of instruments that function as modern stethoscopes, satellites mapping albedo and chlorophyll, ice cores and sediment cores archiving atmosphere and ocean chemistry, flux towers counting the breath of forests day by day. But technological capability is only half of the practice. Listening requires patient institutions that commit to continuity, the social will to fund and maintain long-term observatories, and cultures that prize intergenerational memory over short-term gain. Philosophically, listening implies humility, an acceptance that human perception samples only a thin band of the planet's. Respiration in that interpretation is necessarily provisional. That humility should be codified in public practices, robust, transparent monitoring networks, open data that can be interrogated across disciplines, and a public education oriented toward long-term literacy in Earth system dynamics. To listen is to transform sensing into a public conversation about thresholds and trade-offs, not merely into technical alarms that fade with the news cycle. Closely allied to listening is the ethic of adjustment. If a cough is heard in a lung, the response is to reduce exposure to the irritant. The planetary analog requires immediate and sustained reductions in forcings that alter atmospheric composition rapidly. The near-term imperative is to slow and then reverse the flow of ancient carbon from deep stores into the atmosphere. That is a scientific prescription with moral contours. It carries questions of fairness. Who bears responsibility for emissions generated in the past? And who must pay for decarbonization today? The philosophical posture must combine the precautionary principle with distributive justice. Action must be proportionate to both contribution and capacity, and it must be framed not as sacrifice for its own sake, but as stewardship that sustains the conditions under which meaningful human life, art, knowledge, community can continue. The third recommendation is structural. Reinvent the institutions that mediate between short human time and the planet's patient breathing. Ancient systems of governance were never designed to hold the kind of temporal responsibility that deep time stewardship demands. New forms of institutional memory are needed, fiduciary arrangements that treat ecological functions as public trusts, legal mechanisms that bind generations, and economic accounting that internalizes the long-term costs of atmospheric and ecological damage. This is not merely technocratic tinkering. It is a reorientation of responsibility from actors who benefit immediately to custodians who accept long-term obligations. Such institutions must be plural and polycentric, local nodes practicing restoration and adaptation, regional bodies coordinating water and carbon budgets, and global frameworks allocating the burden of avoiding irreversible thresholds. The lesson is simple. If the Earth's lungs are distributed, so must be the responsibility for their care. A fourth philosophical proposal concerns repair and restoration. Restore the planet's alveoli. The analogy must be treated carefully. It is not poetic escapism, but an ecological template. Wetlands, peatlands, mangroves, seagrasses, and old-growth forests are functionally large surface areas that conduct gas exchange, sequester carbon, buffer against storms, and host biodiversity. Protecting them is both conservative, preventing further loss, and restorative, actively rebuilding lost exchange surfaces. This restoration should be strategic and informed by geologic sensibility, protecting deltas and coastal shelves that sequester organic matter, re-wetting peatlands where carbon has been drained for agriculture, and replanting corridors that maintain hydrologic and atmospheric connectivity. Technological fixes may play a role. Carefully designed carbon removal systems, habitat engineering, but philosophy must counsel moderation. Intervention should strengthen natural processes rather than substitute for them. Fifth, adopt a temporal ethics grounded in deep time. The argument is not abstract. The carbon cycle, the silicate weathering thermostat, and the slow sequestration of matter into sedimentary stores are processes that require centuries to millennia to rebalance. Decisions made in one generation can be legible in sediments and isotopes for millions of years. A responsible ethic would therefore introduce design principles into public choices, avoid actions likely to push system components past poorly reversible thresholds, privilege resilience that preserves optionality for future generations, and cultivate humility around interventions whose long-term side effects are poorly constrained. This is not an injunction to stasis, but a governance imperative to weigh intensity and longevity. It asks societies to ask not only, can we do this, but should we, given the geological ledger? Sixth, cultivate cultural practices that attune humans to planetary rhythms. Science provides signals, culture provides meaning. Rituals, stories, calendars, and arts that recalibrate human imagination toward long-term dependency on predictable breaths can transform attitudinal scaffolding. Farming communities that already organize around seasonality offer models, rituals that honor wet and dry spells, festivals that reinforce communal investment in soils and waters, and folklore that embeds ecological knowledge. A modern version of this approach could be civic rituals tied to monitoring milestones, a community's annual audit of local, water tables, or a national day of listening to climate readouts that knit scientific data into lived memory. If institutions create the capacity for listening, culture creates the willingness to heed. Seventh, accept the necessity of fairness and redistribution in adaptation and mitigation. The planetary lungs do not respect borders, but the capacity to respond is uneven. Ethically responsible action requires redistribution, technology transfer, finance for adaptation in vulnerable regions, debt relief linked to conservation, and compensation mechanisms for communities bearing disproportionate climate burdens. This is not merely philanthropic, it is procedural justice, essential for legitimacy. If stewardship is to be a collective project, it must be anchored in equitable frameworks that recognize historical responsibility and contemporary vulnerability. Eighth, preserve and cultivate memory. The planet archives its own breathing in rock, ice, and sediment, but those archives reveal chemistry more than culture. Human societies must therefore invest in their own archives, in institutions, libraries, and knowledge stores that translate scientific records into social instructions passed across generations. Museums, data repositories, oral histories, and legal precedents must be built to endure. The task is not merely to stash data, but to ensure interpretability, metadata, redundancy, and institutional continuity so that future readers can turn raw chemical signals into reasoned action. Stewardship of the archive is as important as stewardship of forests and soils. Ninth, practice precaution in the face of uncertain technology. The allure of bold, fast fixes, geoengineering, rapid carbon sequestration using untested pathways, can be powerful. Philosophy counsels restraint, prioritize interventions whose side effects are well understood and reversible, avoid technologies that produce dependencies or geopolitical coercion, and deploy experimental approaches only within governance regimes that are transparent, accountable, and equitable. The moral calculus must include potential harm to non-human life and to future human societies, not only aggregate efficiency measured today. 10th, reimagine prosperity in relation to planetary breathing. Economic systems have long treated ecological functions as externalities. A philosophical shift would redefine human flourishing in terms of prolonged habitability, valuing systems that maintain steady exchange surfaces, regenerative agriculture, circular material flows, and urban designs that minimize disruptions to local microclimates. Prosperity would be measured not by throughput alone, but by resilience, biodiversity, and the integrity of processes that sustain habitability. Such a reframing alters incentives. It makes long-term repair financially sensible rather than merely morally aspirational. An 11th recommendation is to cultivate adaptive humility, the willingness to change courses when new signals emerge. The planet's respiratory system contains thresholds that may be detected only imperfectly and belatedly. Institutional humility means creating mechanisms for rapid policy learning and reversal without catastrophic political cost. It means establishing trigger points, scientifically informed and socially negotiated, at which precautionary measures intensify. Crucially, humility is not indecision. It is a procedural readiness to act conservatively in the face of irreversible risk. A 12th and final, deeply philosophical prescription is to foster moral imagination that extends beyond kin and nation to the scale of non-human beneficiaries and future humans. The capacity to mourn landscapes never seen, to value corridor connectivity for species not yet studied, and to hold regard for atmospheric compositions that will persist after one's own life requires ethical cultivation. This moral widening is not sentimental, it is practical. It shapes policies that reduce destructive pressures on exchange surfaces, encourage restoration, and embed the stewardship of planetary breathing into civic identity. The aggregate of these recommendations is not a utopia. They are, rather, a framework for humility and action. They recognize that humans are both fragile inhabitants and potent agents, small cells capable of helping to keep a lung functional, or, if heedless, of clustering into a tumor that chokes the tissue. The metaphor is not meant to moralize the Earth. It is meant to clarify responsibility. If the planet breathes without intent, humans breathe with the capacity for foresight and moral calculation. There is a final, practical, philosophical hinge: fidelity to thresholds. Listening and adjustment must be calibrated to the limits beyond which the planet's breathing changes in character. When permafrost transitions from sink to source, when ocean circulation patterns reorganize, when regional monsoons reorganize. These are the cliff edges where action is urgent. The philosophical question is thus also a timing question. When do precautionary measures move from optional to obligatory? The answer will be contested, But the ethical default ought to be conservative. Avoid actions likely to push systems irreversibly. Protect and restore the surfaces that mediate exchange. Share burdens fairly among those who can afford to act. In the end, the central injunction is deceptively simple. Listen, adjust, help. Listen with instruments and institutions, with a cultural humility that recognizes the thinness of human perception against deep time. Adjust behavior in ways that reduce the intensity and speed of perturbations, cut emissions, curb land conversion. Design cities that respect microclimates. Help by restoring and protecting the planet's exchange surfaces, wetlands, forests, oceans, the functional alveoli that give a planet breath and habitability. These acts are not separate technologies or policies, they are a coherent posture, an ethic of stewardship aimed at maintaining the rhythm upon which human projects depend. The choice is not binary, it is a continuum of practice and imagination. The more listening is institutionalized, the more adjustments are made equitably, the more restoration is undertaken, the more likely the planetary breath will remain within a range that nourishes life rather than stifling it. There is tension here, between the scales of urgency and patience, between localized sacrifice and global continuity, but there is also possibility. A last, almost tender thought: the planet's respiration is not a landscape to conquer, but a condition to accompany. The proper attitude is not ownership, but attendance. This is not passive resignation, it is an engaged, disciplined, moral craft. To learn to hear the planet's breaths, to read their changing color and cadence, and to act with humility in response, that is the profession of stewardship. It acknowledges awe and grief in equal measure, but it insists that all be translated into care and grief into repair. The lungs will continue to work in rhythms long after any single human generation. If humanity chooses to be a cooperative tissue rather than a destructive presence, the record that deep time reads will not be merely the scars of a brief noisy experiment, but the traces of a species that learned to listen and to help the world breathe on.